Hello everyone, and welcome to this first video that will be part of a series about the Go programming language, also known as Golang. And in today's video, and in this first video, we will talk about Golang in general as a programming language and why is it used in the first place, what are its strong points, and also we're going to write our first Golang program that will be a Hello World program. So first of all, let's explain what Golang actually is. Before we actually start the video, notice that you do not need to have a prior programming experience to follow this series. In fact, you could have never programmed before and you could follow this series along just fine. The only rare cases where I will mention some other programming languages, I will never mention their syntax or how they work, but just generally make some comparisons when you will understand the concepts going throughout the course. So there are basically no prerequisites for this course in terms of programming. And in fact, now you can see the structure. We will explain it briefly later, but for now let's just talk about Golang. So since you need not, of course, to understand programming before watching this video, I will also explain some programming concepts that relate to all languages. So let's give a definition of what Golang is. So Golang specifically is a compiled, statically typed language. And well, let's first go through these two properties of the Golang language. And so the first one, it is compiled. And so we're going to explain what these things are, because of course I'm not assuming that you already know what these things are. So even though maybe you have never programmed in your life, you might understand the fact that computers actually communicate, that computers kind of speak the language of binary digits. So they understand strings of binary digits, okay, of zeros and ones. And of course, to communicate with a computer, you need to furnish the computer some instructions in this format. Okay, but the programming languages that we use every day, we all know that they use a language that is understandable by humans, so humanly readable language with instructions such as print and so on and so forth. And so how do we convert this humanly readable language into binary code? Well, this is done by basically because it programs that. And so the process that translates the language, the humanly readable programming language inside into the machine code can differ. And this is why here we specify that Golang is compiled, because there are two main types of languages, and these are interpreted languages and compiled languages. Let's explain compiled languages. So compiled languages, and examples of compiled languages are, for example, C and also Rust, and in this case Golang too, but there are many other compiled languages. What they do is basically, imagine we have your code. This could be Golang code, C code, or whatever other code that is humanly readable that we have written to be executed. Then our code basically gets passed into a compiler, and this compiler turns this code into machine code that the machine understands. So this is fundamentally how a compiled language works. However, notice that the process of compiling alone is extremely complicated and complex. And of course, this is only a very high-level view of what happens. But this is all we need really for now. And what about interpreted languages? So interpreted languages, on the other hand, instead of being compiled directly by, again, a program like the compiler that takes the code and turns it into binary code, it basically, the code that we've written, on the other hand, gets taken by a program that then executes the code. And an example of an interpreted language is, for example, Python, or Lua. And also now I think it is the time also to give another distinction about languages, because here we said that Golang is a compiled, well, statically typed. We'll come to it later. Actually, let's forget about this word for now. We will explain it in the later videos. But Golang is a compiled statically typed programming language. And now there's another difference that we want to make about languages, and that is there are scripting languages and programming languages. Programming languages, and this again I'm giving very simple and practical definitions, and these are not textbook definitions, of course. Just like the definitions that we gave for interpret and compile languages, actually a little bit more technical than that, but I'm trying my best to be to use a simple language. Well, programming languages are languages where there is an entry point, we could say an entry point function, usually called main. And examples of programming languages are Java, C, and Golang. Why? Because, for example, here we can already see in our Golang program that we have this func main. And, well, and for example, let's give an example in C. In C, for example, we have our int. In fact, for example, also in C, we have a main function inside which we put all our code that needs to be executed when we compile a file. And you might ask, well, okay, especially if you have never maybe programmed before, you might ask, okay, well, but then what other types of languages are there? And another question that might come from another viewer that maybe has used Python or JavaScript before, he might ask, well, for example, in Python, I do not need to insert a main function or maybe in JavaScript to execute the code. It just executes from top to bottom. Then how do these languages work? And well, these are called scripting languages. And examples of them are exactly Python, Lua, and JavaScript, for example. And why? Because these languages basically do not have a main function entry point. So when, for example, you just write in a plain text in a file, you just write, for example, in JavaScript. If you have never used JavaScript, don't worry about what this means. But if you create maybe a file, file.js, and then you write inside it console.log hello, and you execute this, you use maybe a node to run this file in the terminal, you get hello. But this, of course, would not work inside C, because you would not tell, for example, for C, you would have not told the compiler where exactly is the main entry point. And now to clarify another thing, notice that here we talked about scripting languages. We said that Lua, Python, and JavaScript are scripting languages, and that Java, C, and Golang are programming languages. But do not fall into, do not erroneously think that scripting must in some sort imply interpreted, or that programming must imply compiled, because this is actually not the case. We can actually find some counter examples in both cases. One of them might be Java, because, well, Java is a programming language, but it is not compiled. So, and well, so it is actually, there's a more technical word for it, but let's not go into it. It's called byte compilation, but let's ignore it for now, because I wanted to keep this this video more, we could say, open to everyone. So with this said, I think that at this point you have a small map in mind of programming languages and what the difference about compiled languages and interpreted languages, and as well as also maybe you now understand the difference between scripting and programming languages. If some of the words that I've used are not yet very clear to you, it's completely fine, because of course programming is one of those cases where you learn pretty much 90% by doing and not by actually studying stuff. And so you will learn then by practicing and getting your hands dirty by coding. So this is the best way to learn stuff in programming. However, at this point you might still have a question in your mind, and that is, well, but then what is the advantage of a language being compiled over interpreted? So in fact, we said already that Golang is a compiled language, and this is one of its key strengths, in fact, because it allows Golang to be a very fast language compared, for example, to uninterpreted languages like Python. And in fact, you might ask, well, but why is Golang, being a compiled language, why is it faster, for example, than Python? Well, because Python, and we will look at from a very high level at the compilation process, at the interpretation process that Python goes through, and in particular we have our Python code here. The Python code gets translated into C code, and then the C code gets compiled. And as you might guess, this is of course more time consuming than just compiling your code directly. Not only that, but also Python is a language with garbage collection and dynamically typed, and this also makes the language even slower. Golang, as we will see, is statically typed. That helps a lot with compilation time. However, Golang still has garbage collection, and we will explain what these terms are, so don't worry if you don't understand yet what they mean, but we will see that even though Golang is garbage collected, and it has still very, very fast performances, because it's one basically of its key strengths. So before we actually jump to the code, I want to mention where I am at the moment. And in particular, here I am inside the website known as the Golang Playground, that I will leave in the description. That I will leave also in the description. But the link for the site is the following: play.golang.com. So why am I using this? Well, because at the beginning, since the stuff that we will be explaining are pretty simple, we do not need a development environment, a local development environment installed on our computer, and therefore we will be fine using this website. And so, with this said, I think we are now ready to explore the structure of this program. So now, of course, while I will go through this program, I won't explain super in depth what each line of code does, but I will just give a quick explanation. So the first line that we see is package main. So this is and also before we can proceed, in Golang you can comment the code using these two slashes. And in fact, you might have noticed that before I was writing all that stuff using these two slashes, or sometimes this other type of comment. And well, you might ask now, why would we want to comment our code? Well, and what is a comment in the first place? A comment inside our program is simply some text that do not get executed. In this case, the compiler just skips it. He does not care about it. So we can use it to, for example, elucidate the instructions that we have inside our code. So for example, if we have here this import statement, we could say we are importing font. So this library, there's a little bit of, and well, also the pronunciation of this library is a little bit a debate, we could say. So there are most people pronounce it as font. Some people just pronounce it format, because, well, the font here name comes from format, because it basically it imports input output capabilities as well as string formatting capabilities. We will see what these things are later. But just know that this is sometimes very often called font, but sometimes also FMT or format. So for example, here in this line here, import, we might comment we are importing the font library. And so this is how we usually use comments. But sometimes comments, when we will see when we maybe have an error in our code and we do not want to delete the line, we might just comment the line out, so that we will basically delete the code for the compiler, because the compiler will just jump it, but we will still have it in our code, and we will not have it deleted. So if we want to maybe restore it, we just need to remove the comment. And as I mentioned before, there's another way to make comments, not only with these double slashes, but you can also do it with this slash and then a star, and then of course close it. And this is for multi-line comments, because if you do a comment like this, so say comment, then in the next line it will not be commented. So if you do this, this will throw an error. But if you comment with this multi-line comment, so I'm going to say multi-line comment, and on the next line we will also have a comment, so this will still be part of the comment. So this is still part of the comment, and this also, and so on. So this is how you make a multi-line comment. So with this said, as promised, let's go through the structure of this program. So at first we say package main. We will see what packages are in Golang, but for now just know that every program needs to be in a package. Then we are importing the library that we said font. So here we're importing a library which is basically a bunch of code that is already pre-written for us, and font library in particular is the library for input, output, and string formatting. And we will see what strings are later, For now, input output, you probably already know what that means. It just means taking input from the user and then returning output to the screen, maybe, for example. In this case, printing out values to the terminal. So this is basically an interface. Then here we have our definition of our function main, and as we will later see what functions are, and so do not worry about the func keyword for now. Then we have the main function, the main name here, which is again what we mentioned before about, well, programming language, about the entry point of the program. And in particular, main just tells the compiler that everything that will be inside here, once we compile the program, will be executed. So in this case, the compiler will know that everything inside these curly braces here will be executed. In particular, this is the line thump.print line hello playground. So in fact, if we try to run this program, it yields the string hello playground. Also to explain what the thump print line hello playground does, and in fact you have seen it now that we have run the program, it precisely prints out the string hello comma playground to the, and so this is the function, so this is the instruction that tells the compiler to print inside the terminal the string that we want. So for now, just think of a string as a text, so a concatenation of characters. So this is a string, just a concatenation of characters. Comma playground, so hello playground is an example of a string. And however, be careful in this case that if you try to write inside the println function hello playground without the quotes, we will get an error, because of course to tell the compiler that what we insert in the function is a string, we need to put these quotes. So always remember that strings always need to be inside these quotes here. So with this said, I think that for this tutorial we said enough about the Go programming language. In the next video we will look at variables. So variables are a very important concept in all programming languages. And so let's define first what variables are in general in all programming languages. So when you write a program, you work a lot with information. And information, as we also discussed in the last video, is stored in our computer under the form of zeros and ones. In our program, however, since we are working with a high-level programming language, we will be working with numbers and with strings. We define what a string is in very simple terms in the last video, and with other type and so on. And still, however, something persists. When we work with data, and that is could be a string, so let's call it, but for now, a word, so like hello, or we might have a number 25 or under the number 47. Sometimes we want to assign a name to one of those values, and sometimes on the other hand we might want to have a label that we can update throughout our program. So for example, imagine we're writing a program that checks how many times a person has clicked on a button, and well, we might imagine to have a number that counts that, and that number should be updated every time that a person clicked on a button. And for example, we might want to call this variable with a name, and we might want to call it count, and then we might want to update it every time, so we might want to change the value that is stored inside it. So a variable is precisely that. It's basically we could see it as a box inside of which we can put a value that can be of various types. And again, a type is just a type of data that we can put inside a variable. And in the first video, you might recall that we said that Golang was a strictly typed language. What this means is that in Golang, whenever we define a new variable, then we have to specify its type. So if we define a variable, for example, our counter variable should be a variable of the type of a number type, in particular an integer. On the other hand, if you imagine we have a variable that stores the name of a person, then we might want a variable of type string. And so not only we have to specify the type that a variable will assume in the program, but we also cannot change it throughout the program, meaning that if we declare a variable that will store an integer, then that variable will only be able to store integers throughout the whole program, in contrast with languages, as we mentioned in the last video, such as Python. And again, if you have never used Python, don't worry about it, but in Python, basically can declare a variable without stating if it will store an integer or a string or whatever other sort of data, and then throughout the program you can update it to even to a different type of data. In contrast, as we said before, in Golang we will only be able to update a variable that we declare, for example, as integer to other integers. If we, for example, set an integer variable to a string, then we will get an error. Now that we have understand conceptually what variables are, so again, they're basically we could see them as box with the labels on top of it, which help us in many ways. So one way we said already is that we're giving a name to a value, so it's easier to access it during the program. Another thing is that it's a label that contains a value that we can then update inside the program. We can modify, we can access it, and so on. And so these are all uses of variables, and this is why they're so important in programming. But now let's see how to actually define a variable. So in order to define a variable, the syntax is the following. It will be var, and this is a keyword, it means variable, shorthand for variable. Then we will say our name of our variable, and this is arbitrary. This is what's called an identifier in a programming language. It's basically, and in this case it's arbitrary, we can call it whatever we want. We can call it name, name1, name2, we can call it, for example, number, I don't know, whatever you want. And however, be careful that there are some rules about naming that we won't go through now for simplicity. And they vary from programming language to programming language, but they're mostly similar. But for now, let's maybe call it number1. Once we have set var, the name of our variable, then we want to specify its type. In this case, maybe we might want to work with an integer. And the type for an integer is, the keyword for an integer is int. Once we've set this, we now set the equal operator to assign it a value, and we maybe set it equal to 1. Creates a variable called number1 that we can access throughout our program. So let's now write a comment that gives the general format for an instruction of this type. So to create a variable, and that is the following. It is var, then the name of the variable, then the type of the variable, and then the equals the value. So this is the syntax for creating a variable. So now we can use and access this variable throughout our program. So imagine we want to print this variable. We can insert it inside the println function, and by running our program, it gets print out to the terminal. So we might now want to change it. We might set it equal to 55, and as you can see, it will get printed out 55. So now you might have a question. What gets printed to the terminal? Is it a string or is it an integer? Maybe this might confuse you at the beginning if you have never programmed before, but the answer to this is actually what gets printed out to the terminal is a string. So even though here we have inserted a number of an int data type, the value that gets printed to the terminal is a string, so it's basically a concatenation of characters. So in the terminal, the data that the user and we will say the data exchange between the user and the program, so the input you insert and the output you receive, are actually strings. And what does it mean to be a string? It's basically a succession of alphanumeric characters. And these alphanumeric characters are actually encoded by bits, so by sequences of bits. If you're interested in how this works specifically, you can look up an ASCII chart, and you can see how numbers get mapped to letters and also other characters. For example, also to other numbers, of course, because in the ASCII codification, for example, 48 gets mapped to the character 0. But we won't cover how ASCII and how strings are saved in memory in depth in this course, because of course this is a introductory tutorial to the Golang language. So we will just mention this. So we will just mention that, well, in the terminal, when you print out a number like this, we pass a number, an int type, to this println function. What gets printed in the terminal is basically a conversion of this variable into a string type. And again, in this string gets printed out in the terminal. And so, with this said, we are now ready also to introduce some new data types, because I'm sure that at this point you now know how to declare integers. So these integers can also be negative numbers, for example. Okay, let's print both now. Now notice that in the println method, when you insert a comma, the two numbers that we printed get concatenated and a white space gets added in between. So in this case, we printed out 55, then a white space, and then minus 55. This is how it gets formatted when we print with println. So we now can work with integers, both negative and positive integers. But there's a problem. This is pretty limiting because sometimes, well, we want to work with, of course, with maybe with decimal numbers or with strings. So with basically, we could say words, etc. So how can we do this? We define a variable of another data type. In Golang, there are many other data types. For example, the data type that we use in order to work with decimal numbers is called a float. And float stands for floating point number. This refers to actually to the way in which they're stored in memory, but we won't, again, this is another thing that we won't cover. So just know that float is basically means decimal number. So if we want to define a float, we will use the same format, the same syntax as before. So let's say bar number 2, but this time float 32. Oops, 32. And maybe we could set it equal to 3.15. We can set it equal to 3.14. And we can maybe create another floating point variable, float 32, equal, and set it equal to minus 8.7. So these could be two examples. So now we can print them out. And let's see what we get. Okay, and this is what we get. In this set, we now have introduced floating point numbers and integers. But there's also another important data type that we will work with, and we introduced it in the last video, and that is the string. So for now, let's remove these variables that we created here. So suppose that we want to create a string. Maybe we want to print to the console hello world, for example. Well then, to declare a string which contains the value of hello world, we will just define it as follows. We could say var, we can call it message, maybe message, then string, which is the data type, and then we set it equal to hello world. And then we just pass this message inside the println function, and let's see what happens. We get hello world in the terminal. Now I want to expose you to one of the first errors that you will encounter pretty often in Golang, and that is, let's try to basically print something out, so maybe hello, and let's basically leave this variable that we defined unused. So let's try to run the program now, and now you see we get an error. It says message declared and not used. So what happened is that the Golang compiler saw that here we define a variable that, with name message that we do not use throughout the program. So basically this variable is just useless and it just occupies space that it does not use. So now let's try to comment this out, and we see that then now the program works. So basically this is another good feature of Golang, that basically it tells us whenever we declare a variable that we didn't use. This also works with imports. When we import a library that we do not use, we will get an error. So but we will see importing and packages later, so for now don't worry about it. So now the last data type that we will cover in this video is the Boolean data type, and where a Boolean data type basically can assume only two states, and that is false or true. And these Boolean data types are very, very important in programming because you can use them to check for conditions and other things. And we will later see how you can work with Boolean data types also to make selection instructions. Selection instructions are basically instructions which can tell us how to basically, they can tell us what to do based on a condition. We will later introduce them when we will talk about them in the future videos. For now, just know that a Boolean data type is something that can be false or true. For example, we can say var is maybe older than 20, and you can put this equal to a bool, and we can put it equal to true. And for example, we can also say var is older than 25, bool, and we can put this equal to false. So print Boolean data types to the console. So for example, if we print is older than 20 and then is older than 25, then let's see what we get. As you can see, we get true and false. And again, here we have white space in between because the println function automatically adds a white space in between when we concatenate two values inside it. So with this said, I think that we covered enough in this video, and in the next video we will start looking at some other ways to print out stuff to the console using other methods of the FUMT library. In this video we're going to look at the output functions of the FUMT package, also known as format or FMT. And in particular, we're going to look at three very important functions, and these are, I'm going to write them already: print function, the println function, and the printf function. At this point, you should be a little familiar with just one of these, and that is the println function. So this one. And you should probably understand that this function is responsible for outputting stuff out to the terminal, but maybe nothing more than just that. And to this video, I'm going to actually explain what the println function does a little bit more in depth, and then also see what the print functions and the printf functions do and how they differ from the println function and why we would want to use them. So we're going to start with the print function. And the print function essentially just outputs the value we pass in to the terminal. So just like the println function did in the last videos, but there's a difference. If you probably recall, when we used also the golang program website, and also as a notice here now I switched to a local environment just because the syntax is highlighted, and maybe you can see the code better, but you can still use the golang playground website that I left in the description of the video. So I actually advise doing that because so that at the beginning you can focus more on the programming concepts and not on the installation process of the Go compiler. But with this said, the print function just outputs something to the console, but it does it in a slightly different manner than the println function. So if you recall, when we used the Go Playground website and we printed out something with the println function, we will get a new line after it. You see the value that we passed into the println function, and then basically the new terminal line on a new line. However, let's see what happens with the print function. So let's try to print something like hello with the print function. And let's also comment this out, but let's print that with the println function. So I'm going to say we're going to print the same thing. So let's try and run this program with the, first with using the print function, so printing out to the console the hello string with the print function. And let's see what happens. In particular, if we say go run output.go, let's see what we get with hello, but it's on the same line. Now let's try to do the same, but this time with the with the println function, and we will see that basically we get hello on and then the next terminal line will be on a new line. And fundamentally, what the println function does more than the print function is just adding a new line at the end. And however, we can actually achieve the same result with the print function just by using a character for the new line, and that is the new line character that is encoded in ASCII also. And the way we achieve this is via what is known a escape character. In particular, the /n escape character. This basically encodes a new line in the output basically. So we can now try and add a new line to the hello string that we passed into the print function, and let's see what it does. So if we say go run output.go, then we get hello on the new line, even though we use the print method. So what if we want to insert multiple new lines? Well, then we can just add multiple escape /n escape characters, and running again our file yields hello with this time 2 new lines other than the other one that we included before. So this is basically what the print and the println function do. Basically, they print out stuff to the terminal, but the println function has a new line inside of it. If you have used Java before, then it's basically the same as Java. But if you have not used Java, don't worry about it, because of course, because this video is supposed to be accessible to everyone, even with no prior programming experience, of course. So with this said, we now have covered 2 of the 3 functions that we promised to be looking at in this video. The third one is called the printf function, also known as the print formatted string function. So in the last videos, we also saw how you can pass in variables inside the print and println function to make them print out to the screen. So suppose we had like a variable, a string, for example, such as name, type string, and equal to John, for example, and then a var name2 string equal to Jack. Then if we set from println name and name2, then by printing this out, we will get John Jack separated by a space. But what if, imagine we want to immerse these 2 values, which of course are variables, and that they might change throughout the program. Maybe, for example, suppose that this was not a name, but maybe it was like a score. So for example, a score of integer type, maybe equal to 15, and then you had here score, for example. Let's run this. You will get 15 Jack. So you could say Jack has scored 15. The score, of course, can change throughout the program, because imagine you're trying to write a game, maybe of some sort, and then the score gets updated every time a player does something. And well, then suppose you want to print something out which is dependent on one of these variables, which might change throughout the program, and you want to print it in a certain format. So for example, you might want to print I don't know, like player name, and here I'm using the curly braces to say like the value that it should be placed there, but based on a variable. So maybe the player name, and then has score, and then insert the score. Okay, but one way which you can do that, and it's actually it could work, it is basically say, okay, then what I'm gonna do is I'm gonna say player name, so name2, then I'm gonna say has score, and then I'm gonna insert the score. And you can see that if you run this, it says Jack has scored 15, and it actually works. However, another way to tackle this problem is by using the printf function, which is the following. And the printf function actually does the following. It takes in a formatted string, and then as the other parameters, it takes the variables that you use to format the string. So I'm going to try to explain me a little bit more clearly. So basically, the printf function, the goal of the printf function is to return a string of format. So basically, a format inside of which you might have values that depend on variables that can change throughout the program. Something like the example above. And so in order to realize this, the first thing that you need to pass in is the format. So the type of, we could say, string expression inside of which you want to immerse your values, you could say. And so the first argument is a formatted string. Then in this formatted string, you might want to insert many variables, many values of variables. So many, you could say, values that depend on variables, and you need to pass them in, because of course otherwise the function, the program, would not know which variables to insert in which spot. So the general syntax is the following: it is from printf, then a string of format, and then variable 1, variable 2, and so on, up until variable n, you could say. Okay, but now one question stands. How do you tell the printf function where to put which variable? Because at this point, I'm sure you understand that the printf function basically takes a string of format, and then it says, okay, at this spot, you take the value of this variable and you insert it here, and then the other one you insert it somewhere else. But how do you say exactly where to insert each one? And well, we do this we use formatting verbs. And there are many formatting verbs in Golang. Maybe we will see all of them in the next video. In this video, we're gonna only see a couple of them. And these are the following. So the first one is the %v formatting verb. And the %v formatting verb basically says to the printf function, here you can insert the value of the variable. So it basically, if you want to be more technical, it inserts in the formatted string, in the output, the value in a default format, because there are also other formats to represent a value of a string. We will see it in the next video. Then the second formatted string that's very important is the %T formatting verb. And this formatting verb basically gives a Go syntax representation of the type of the value. So basically, we're gonna look at examples of both of them, because I'm sure it will become immediately clear what they do once we see an example. But for now, as an explanation, I'm basically gonna give the following. So the %V basically prints out the value of the variable inside the formatted string, whereas the %T formatting verb prints out the type of the value. So suppose we have the following formatted string, or the following formatted verbs. So we want to print out, remember our goal was to print out player name has score 15, for example. Jack has scored 15. Okay, then let's insert a formatted string, which is just a string. But now what I'm gonna do is I'm gonna say, okay, the first spot here, we have this placeholder player name, okay, where we would want to insert the value of the name name2 variable. So what do? We go here and we say %v, which is the formatting verb for the value of a variable. Then we say has score, and then %v again, and then what we do, we pass the variables in order that we inserted inside the formatted string. So this will be name2, and then score. Now let's see what is the result of this. So if we try to run it, output a go, then we get Jack has scored 15. So if you want to make it a little bit more pleasant, then you can maybe insert a new line character at the end, and you can get the following output: Jack has scored 15. Okay, but this is how you can use the %v formatting verb. What about the %t? Let's try to use it in this example. So what if we insert the %t formatting verb in place of the first %v formatting verb? So let's do it like this. Let's see what we get. And what we get, string has scored 15. So we got the type of the variable that we inserted. And as I said before also, notice that the verbs are in order, meaning that the order of course matters here. Because if you try, for example, to substitute this name2, for example, with score, which is of int type, and then we change and we insert name2 here, so we switch the order, then of course the printf function takes the first variable that we inserted and puts it in the first, we could say, formatting verb spot. And now let's see what happens. And we get hint as score Jack. In fact, the type of the first variable that we inserted, which is score, in this case, is an int, is an integer. So with this said, we have seen two of the most important formatting verbs for the printf function. But actually there are more. And the last one which we will see in this video is the %v formatting verb. And this returns a Go syntax representation of the value. So let's see what we mean by this. Let's substitute the %t formatting verb with the %v formatting verb, and let's see what happens with the score value. So let's see, and we get 15 as score Jack, which is a representation of the value of int. And let's see what happens on the other hand with name2. So if we insert name2, and notice that we can insert the same variable many times as you want, as long as you don't forget to comment out the variables you don't use, of course. So we get Jack has scored Jack. As you can see here, the using that other formatting verb printed out the string, also including the quotes. And this is why it's called a Go syntax representation of the value. However, for now, it might be a little bit confusing, the difference between the %v and the %v formatting verbs. So for now, don't worry about them, and I'm sure that will be clearer once we will introduce structs. And I'm sure you'll also see why that is the case. So with this said, I think we've said enough in this video, and in the next video, as promised, we're gonna look at other formatting verb language. And today we're gonna look at some other important formatting verbs for the printf function of the font package. In particular, we're gonna start with the integer formatting verbs. And integer formatting verbs are basically formatting verbs that you use to include the values of integer variables inside a formatted string. So let's try to declare an integer variable that can be, we can call I, and of int type. I'm gonna set it equal to 5. I'm gonna declare another one called j equal to -7. Okay, now let's use the printf function, so font printf, and then now we're gonna look at the first formatting verb that we will look in this video, and that is %d. So formatting verbs, the %d formatting verb. So the %d formatting verb includes the value of an integer variable inside a formatted string in a decimal notation. So I'm gonna say includes value of a variable in decimal notation. So maybe you are familiar with decimal and binary and hexadecimal and octal notation. If not, I have a video on the channel that covers the octal and binary notation. But if not, don't worry too much about these formatting verbs then for now, but just know that they are a thing. So the first one, of course, prints out the number in the usual decimal notation that we're all accustomed to. So for example, actually let's just work with one number, and let's set this number equal to 541, for example. Then basically passing in the I variable inside the printf function yields go run auto.go 541, which is again the decimal, the usual decimal representation of our number. But as I said above, also there are other of course bases to represent numbers. One of them, for example, is binary, which is very important in computer science. And to represent a number in binary in a formatted string, we use the %b formatting verb, and this includes the value of an int variable in binary. So let's try it with the 541 example before. Now let's see what it yields. And the result is 100000011101. And in fact, if you're familiar with binary notation, you can try and calculate that the two numbers are actually match. You just have to basically raise 2 to the power of the place it is in that string, and then sum all of them and multiply it by the digit that is placed in that in the string. So for example, if you have 101 in binary, this in decimal is just 1 times 2 to the 0 plus 0 times 2 to the 1 plus 1 times 2 squared. So this is just 5. And maybe even if you have never used binary before, with this we could say empirical introduction to the binary system, you could have understood how binary works. But I think it maybe requires a little bit more time. So another important formatting verb for integers is the %o formatting verb, which includes the value of an int in octal, which is another base. It just means base 8. So for example, let's try and do the same thing with the previous example, and we can see that the result is an octal, which is 1035. And in fact, 541, if you calculate it, is nothing but actually 5 plus 8 times 3 plus 8 to the 8 cubed. You can do it with a calculator, and you can see that that is the case. And also another very important one is the one for the hexadecimal. Hexadecimal is also very important in classical digital computer programming, because while with digital binary computers you work a lot with numbers in base 2, in base 8, and base 16. And the following formatting verbs are used to represent a number in hexadecimal. So the %x is used to represent a number in base 16 with lowercase letters, whereas big X is used to represent a number in base 16 with uppercase letters. So now let's declare another variable. So for example, j, int z is equal to 987, and let's print both of them in hexadecimal. So both in uppercase and in lowercase, and let's see the difference. Oh yeah, sorry, I forgot to include the number twice. Of course, the printf function doesn't know what to include if you don't pass enough variables. So on accident you also got exposed to the... Okay, so as you can see, with the first formatting verb we got the hexadecimal number in lowercase, whereas the second representation is in uppercase. So with this said about integer formatting verbs, I think we're now ready to move on and also look at string formatting verbs, and also as well as formatting verbs for other types. So let's start with string formatting verbs. And actually there's only 2 important string formatting verbs that you have to keep in mind, and that is the first one is the %s formatting verb, and this just includes the value of the string without quotes, whereas the %q formatting verb includes the value of the string with quotes. So let's see an example. Let's declare a variable that we call str of type string equal to, for example, city, and then another one equal to I don't know, Rio de Janeiro. Okay, so if we now print with a printf function, percentage q, and then percentage. I'm gonna include a semicolon in between, maybe just to emphasize the difference, and then percentage s, then a new line, a percentage q, semicolon, a percentage s, including str, then str2, str2. Then let's see what the output will be. Go around output.go, and the result is city with quotes, then city, and then Rio de Janeiro with quotes, and then without. So as you can see, this is just the difference between the percentage s and percentage q formatting verb. And the last formatting verb that we're going to see is that for Boolean values. So you can also use formatting verbs for Boolean values, and actually there's just one that you need to know, and that is the percentage t. That just includes the Boolean value that is true or false of a variable. So let's, for example, declare a variable that could be is English, and that is a Boolean type, and set it equal to true. Then if we use the printf function and insert percentage t, and then is English, let's see what the result is. Go around output.go, we get true because it is set equal to true. But what about setting it equal to false, for example? Then we will get false. So as you can see, it just prints out the value of a Boolean type of variable. So with this said, in this video we have said enough about all the main important formatting verbs for now. Of course, there are still data types which we haven't covered well enough yet, such as slices, arrays, and we will see what these are, and structs later, as well as maps. And also, I didn't include a discussion on the formatting verbs for floats, because we have not yet covered floats well enough, in my opinion, to start working with them a little bit more. And in the next video, we're gonna look at different types and new ways to declare variables in Golang. That is different from this var type format of declaring them that we have introduced already. And today we're going to look at other ways to create, or actually more formally, declare and initialize variables. In fact, so far we have not yet talked strictly about what initialization and declaration of variables is. And to this video we're going to do exactly that, as well as introduce type inferring. So the first thing that we want to introduce is, what does it mean to declare a variable? So you are probably familiar with the concept of variable as a sort of a box with a label on top that contains a certain value that you can access throughout the program, you can change, you can print out, and so on. But when you create one, there's actually different things that you do. And now let's see exactly what the difference between declaration and initialization is. So declaration is just basically introducing a new name inside the program. Roughly, actually, it's a little bit more than that, because in some languages there's what is known as a preprocessor, and well, it's not super strict. But for this video, for example, here, it is a good enough definition for you to understand what declaration is. So when we declare a variable, we want to say to the compiler, okay, we are going to introduce this new name inside our program that we will use in the future. But we're gonna just say, okay, this is a new name that we will use, but we do not necessarily assign a value to it. And initialization, on the other hand, is the process of assigning a value to a variable. So why did we care about separating these two processes? Well, because we don't actually need to assign a value to a variable each time we create one. We could as well just declare a variable, for example var str of type string, and actually do not put anything inside of it. So say, do not specify anything about its value, and the compiler would just be fine. Of course, remember that Golang, if you do not use a variable inside the program and you declare it, it will throw an error. It will say, you're not using this variable, so you don't need it, comment it out or remove it. So compiling the program as is now, of course, would throw an error, but actually this saying here that we wrote is completely correct in Golang. And what we did here was just declare the variable str, meaning we're telling the program that we're going to use this name inside the program, but we did not yet assign a value to it. And so we understand that we can actually declare and initialize values on separate lines. Basically, we can declare it on one line and then initialize it just after. So we can initialize, for example, this variable to hola. Then if we try it with font to print out str, let's see what we get. And you get hola. As you can see, the program works, and we basically first just declare the variable. So we said, okay, this is the name we're going to use, and then we said, okay, this name is equal to that string. And then now the program knows that str basically is equal to hola as a string. Okay, so this is the first thing that we should have said about variables. Now, as you know, Golang is a strictly typed language, meaning that when we declare a variable, it is very important that we include the type in the declaration. Because if we, for example, forgot about saying that this was a string, and we did this, then look what happens. We will get syntax error, unexpected new line expecting type. So it is very important that we specify to the program that the str variable is of type string. But now let's see what happens if instead we said var str is equal to hola. And now you should notice something weird. Okay, when we said that Golang is a strictly typed language, it's important that we specify the type, but we now didn't specify the type in this expression here, but we still got a variable of type string. In fact, if you're not convinced, let's try to print out the type using the %t formatting verb that we introduced in the last video. Let's see what it gives. So go around, go string. So we got a string, but we didn't tell our program that this was a string. It kind of it basically just inferred it on its own, and this is the concept of type inferring. So also, this is the name is pretty suggestive. It should suggest that this means basically deducing the type of a variable from an expression that doesn't explicitly tell it. In fact, that is what inferring means basically in English. And what we did was precisely an example of type inferring. So we declared and initialized a variable at the same time without specifying its type, and then by setting it equal to something on the right, then the Golang compiler understood what type was it just by looking at the value we initialized it to. So we can do this also with integers. So if we, for example, we said int 1 equal to 55, then we go here and we substitute it with int 1. Now let's see what happens. Go run alpha to go. Oh, actually, sorry, yeah. Well, now you see, also with integers, it basically infers the type by the initialization that we did. So now with these two things that we said, you now should know that you can declare and initialize variables at different parts of the program, so you do not need to do it at the same time. And you can also declare variables without specifying its type, but only if and only if you're going to initializing it at the same time too. Because if you're going to just declare a variable and then not initialize it, and if you don't specify its type, it will throw an error, as we saw above. So for example, doing this var number would not be okay, because we're not also initializing it. We're just declaring it, and when we declare something, we need to strictly specify its type. So speaking again with type inferring, there's also another way to infer a type of a variable, and that is using the colon equal sign. This actually, if you've ever programmed in Pascal, and maybe you like vintage programming language, you should like this because this looks a lot like variable initializations in Pascal. But basically, the syntax in order to declare a variable using the this sign here is the following. So let's write the syntax. So you have your variable name here, then you have this sign here, which is actually in mathematics it is often used as a definition sign. So you define this as, and then here you have the value. And in this case also you do not need to specify the type because it will be inferred naturally by the compiler. So let's make an example, maybe number, and basically we're gonna define it to be equal to 76. Now let's try to printf first the value and also the type of it. Let's see what returns. And we got 76 int. So as you can see, this also works and the type gets inferred. So Also another thing that we should cover is also how to declare more than one variable on the same line, because often you want to declare many variables, but you do not want to use many lines of code, especially when, for example, sometimes it can be good and it can save lines of code, as well as it can also help readability. So first, let's suppose that we want to declare many verbs of the same type. So for example, we want to declare a variable a of type integer equal to 1, another variable b of type integer equal to 2, then c equal to 55, and then d equal to minus 178, minus 178, and then e equal to 768, for example. Okay, so as you can see, this took 5 lines of code, and also it is not super beautiful to look at, because we're repeating the var and int keywords, the var and int tokens a lot of times, and it just looks untidy. So how can we fix this? Well, we can just declare all of them on the same line, and now we can do that, and we can do it in the following way. We can say a, b, c, d, and e int equal to I forgot the values that we put. For example, let's say that we put it equal to 1, 2. I think the first one was 55. Then I forgot the other one, but never mind. And so this is actually as equally valid. And now if we try, for example, to print all of these out, so A, B, C, D, E, and then run the program, you get all of them out. So as you can see, you can also declare variables on the same line like this, of the same type. But what if they're not of the same type, but there's still a lot of variables that would occupy a lot of space, and maybe you want to declare them on the same line? Well, then you have to use type inferring. You cannot specify the type strictly, and to declare more variables of different types on the same line, you can either use the operator of the definition operator that we introduced before, or using var equals with type inferring. So for example, the first way would be var, for example, a, b, c, d, e, and then we set the first one equal to an integer 17, the second one equal to a boolean true, the third one equal to another boolean false, and then the last 2 ones are strings. So for example, string 1 and then string 2. So let's see what happens if we run with the compiler our code. The code prints out just fine and it works. The other way to do this, now let's comment this line out, would be to use the definition operation, and that is the following. In this case, we need to omit the var keyword. I'm just gonna include the definition operator, which is this one. It's colon equal, and then we set the same values as before. So 17, true, false, string 1, and then string 2. And this also works, as you can see. And so these are some ways that you to declare variables on the same line. And again, as I said before, this can be useful in some cases in which basically defining a lot of variables on different lines could impact readability of the code. And at this stage, probably, if this is your first time programming, you don't understand quite yet what readability of code means, but you will see what that means once you start building bigger projects. So lastly, you can also declare variables in block using these parentheses. Actually, if you remember on the Golang playground that we used in the last videos, you can also basically group together package inclusions using these braces. But of course, we will cover that once we cover packages import and the package structure for Golang. For now, let's see how you can declare variables in block. So the way you can do it is pretty simple. You just use the keyword var as usual. Then you open some braces, and you can declare your variables. So you can declare them and initialize them. You can, for example, declare them of another type and initialize them, declare them of another type and just declare them without initialization. And this is actually useful because if you recall before, you could just declare on the same line in block variables of the same type. Because if you try to declare variables of different types on the same line, you cannot do that, because you necessarily had to use inferration operators, such as var equals without the type in between, or the colon equal operator. With this, on the other hand, you can also just declare variables of different type in block, and this is also, and you will see that this might come quite in handy sometimes, and it can help with readability. And now the last thing that I want to talk about variables and variable declaration is that of identifier rules. So we already said that an identifier is basically a arbitrary name that you give to, for example, a variable. Now, a variable needs to obey some rules, of course. For example, let's try to declare and initialize using the colon equal operator a variable of equal to 2ab. Let's set it equal to 22. So let's try and print this out. So print 2ab. Let's see what happens. And syntax error. As you can see, it gave us a syntax error because we're not allowed to start variables with numbers. And so we empirically, you could say, experience one of the first rules. So the first one is that a variable name, so an identifier, cannot start with a number. Not only that, but also a variable name must necessarily start with a letter or an underscore character. So the underscore character, this one. And so this is why the previous variable gave us an error. Now let's try to, for example, call it %ab. And let's do the same. And as you can see, it also will give us an error. So if you run it, it will give an error because we started the variable with a non-accepted character. So always remember, use that your variable needs to start with a letter or with the underscore character. Another important rule is that your variable cannot be one of the reserved keywords of the Go language. This will be clearer once we introduce some constructs of the Go language, such as, for example, if, else if statements, and so on. But for example, if you try to declare a variable if, and you set it equal to 23, then if you try to print it out, it will give you an error because this is a reserved keyword. We will see what if statements will do when we will cover them. As you can see here, you cannot declare a variable named if. And then another important rule that you need to obey is that, of course, variable, and I'm sure you've already probably convinced yourself of this because you saw that in this video we only declare variables without spaces, and variables cannot contain spaces. So in order to emphasize, for example, spaces in a word, you can use other cases. You can use some variable declaration formats. So formats to emphasize spaces that are good for readability. I will present some of these notations to you that you can use in your programs to increase the readability of the latter. So the first one is camel case that I'm sure you're familiar with if you use JavaScript, for example, for web development. And camel case just works as following. So for example, imagine you have a phrase such as my name is, but then camel case basically transforms as follows. So it compacts the word, and then it will leave the first word unchanged, and then after each space, the first letter of the following word will be capitalized, but just the first one. So for example, my name and then is. To accustom yourself better to this convention, you can, for example, consider I live in, I don't know, London. Okay, if you convert this into camel case, this will become I then live in London. And this is another example. Another very important naming convention is also snake case, which basically just eliminates spaces. For example, in the last case, I live in London, by adding a underscore character in between. So this would become I live in London. As an exercise, you can try to transform these phrases into camel and snake case. But really, the way in which you declare your variables, the identifiers that you give, is pretty much up to you. These are only some rules that actually increase readability, but you can make your own if you really wanted to. So with this said, I think we've said enough about variables in this video, and in the next one we will start talking about floats, and also in general about numeric types in Go, because yes, we look at integers and we briefly mentioned floats, but in Go it turns out that there are many other numeric types that can come quite in handy in some situations where, for example, you want to occupy less space in memory. So if you want to make a memory efficient program, then you might not want to use int every time. So we will start this video as promised with an introduction to floats. So what are floats actually? So floats in general stands for floating point numbers. And what floating point number actually means, so in this video we want to go like super in depth, super low level into how floats are stored in memory, but we will just give a little bit of important notions about floats, and also we will explain on a high level how floats are stored. So a float again stands for floating point number, and this basically means that the point, the point that basically separates the decimal part with the integer part of a number that is not an integer is stored. So it is not fixed, but it's rather floating. So the use of floating point arithmetic was chosen because of many advantages that it has over fixed point arithmetic. However, one of the disadvantages that floating point arithmetic has over fixed point arithmetic is that floating point arithmetic is considerably less accurate. So this is why often when you will work with floats, and for example you make comparisons between floats or you will sum them, you will notice weird behaviors, and that is completely fine. That is basically inside the we could say a nature of the floating point arithmetic. And so if you maybe had to write, I don't know, a computer algebra system or something like that, and you wanted to have a more precise way to add, for example, non-integer values, then you could probably, if you wanted to, implement your own fixed point arithmetic system. But that will be pretty time consuming also because you will want to optimize it. And as an alternative, you could just use a third-party library. So with this said, we just introduced a little bit what floating point number means. And let's see now how floating point numbers are stored in memory. So we're going to go over just regular floats, because there are floats that are stored in 32 bits, and in Golang these are called float 32, and we introduced it also in the previous videos. But there's also floats that are stored in 64 bits, and these are called float 64. So if you come from C, but again, if you don't know C, don't worry about it, then you would probably recognize these are floats and doubles. But again, don't worry about it if you're not familiar with C. So with this said, let's now see how floats are stored in memory. So now imagine you have a decimal number, such as, for example, 2.5. Okay, then 2.5 in decimal notation that has an integer part that is 2 and a decimal part that is 0.5. So how the computer stores this in memory is in the following. It converts this into binary in the following way. So decimal part just gets converted into binary in the regular way. So it is equal to 1, 0 in binary. And why? Because, well, 1, 0 is just 1 times 2 to the 1, which is 2, plus 0 times 2 to the 0. And this is, as in total, is just equal to 2 in decimal. So it converts 2 into binary, 1, 0. Well then, for the exponent, the process is a little bit different. You basically multiply the exponent by 2 until you get 1. In this case, you immediately get 1, and so this is just 1. And the number 2.5 translated into binary is just 0.1. Another example could be, for example, 7.25. So again, 7.25, 7 in binary is just 2 plus 4 plus 1. So it's basically 1, 1, 1. But 25, so 0.25, what you do is you multiply by 2 once, so 0.25 times 2, you get 0.5. So you take 0. Then you multiply 0.5 by 2, you get 1, and you take 1, and then you finish. And so the end result is 111.01. And so this is the conversion, some examples of conversion from decimal notation to binary. So now we know how we can convert decimal numbers from base 10 to base 2. But now how does the computer store these decimal numbers actually? Because, well, this process of conversion from base 10 to base 2 is quite important in the process of the storing of floats into memory. And we will see now how this actually comes into play. So suppose again we have a number such as 7.25. So already said that this number gets stored as 111 upon 0.01. Yes, it should be 111.01. And now how does the computer actually store this number? So the computer stores this number by separating it into two parts. And these parts are called the significant part and the exponent. Also, the significant part is also known as the mantissa portion. So just as a notice, you will want to know that sometimes, because sometimes it's called mantissa portion. And it allocates a certain number of bits for the exponent and for the mantissa portion, because you know that computers basically store stuff in memory using bits, which is binary, just means binary digits, which is a 0 or a 1. So they store it in base 2 basically. And now, but we do not know yet what these words mean basically, because we say, okay, significant part, exponent, but what even is that? So the definition of significant part and exponent will become clear once we know in which form the computer transforms this basically this decimal number in binary. In particular, it will transform our converted number, which is 111.01, into the following form. So it will basically be 1 point some digits here times 2 to some number. Now, the digits after the 1, so that we denoted with these minus signs, is the manticiple, is the significant part of the number. Whereas the natural number n, that to which we raise 2, is the exponent. And this is basically how a computer saves into memory a bit. So it basically just saves these parts after the 1, and then it saves the exponent to which you raise 2 and multiply the number. In this case, our 7.25 would just be 1.1101 times 2 to the second power. Why? Well, because by multiplying 1.1101 by 2, so 1.1101 by 2 yields 1.101, and then multiplying it by 2 again yields 111.01, which is our original number. And so this is how the computer stores it into memory. And we also talked about that the computer can allocate either 32 bits or 64 bits, also depending on the architecture of the computer, for this floating point number. And for the float 32, it will allocate 32 bits. And these 32 bits will be basically segmented in the following way. We'll have 8 bits allocated for the exponent, and we will have 32 bits allocated for the significant part. And then actually you would say, well, what about the last bit? We now have 31 bits, allocated. What about the last one? Well, 1 bit will be allocated for the basically the flag for the sign, because of course you need to specify if the number that we saved is a positive or a negative number. A flag for the sign is also present for integer values stored in memory. For example, if you store a integer inside of memory, so a value int, where you don't have to worry about all this mantissa and exponent part, you just have an integer, so something like that. Well, the way in which you store it is you say, okay, if it's a positive, I'm gonna set the 1 bit to denote the sign. So if it's positive, it's gonna be 0. If it's negative, it's gonna be 1. And then the remaining, for example, if we're storing a number in 64 bits, the remaining 63 bits will be devoted to the actual number, to the storing of the actual number. So the maximum number that we can store in 64 bits for a signed integer will be 2 to the 63 minus 1. Whereas the maximum number that we can store in 32 bits for a signed integer will be 2 to the 31 minus 1. Now suppose that we only care about the actual value, so the absolute value of a number, and not about the sign. Then we will free basically 1 bit for its storage in memory. And so the range of numbers that we would be able to represent will be from 0 to 2 to the 64 minus 1. And so this is for what are known as unsigned integers stored in 64 bits. And we will see at signed and unsigned integers in this video, because we will cover numeric types. So this is basically roughly how floats work. And for 64 bits, so for float 64, you will have again 1 bit stored for the sign flag, then 11 bits for the exponent, and then 52 bits for the significant. So this is on a very high level, meaning that we do not like dive super deep into it, how the computer stores floats into memory. And if something is not super clear about it, you can just comment in the comments and I will give some clarifications about it. But even if maybe something's really, you really struggle to understand something about this part, don't worry, because you will not need it in your daily programming life, of course, especially at the beginning. But it's good that maybe you just have an idea of how floats work. Maybe just to not, we could say, become discouraged if you ever encounter errors working with them, because you will of course have a lot of errors when you will work with floats and also doubles. So now that we have covered floats, we're ready to see how to declare them in and initialize them in Golang. So the first way in which you could declare a float variable would be to just say var, then its name, which is an identifier, and we also covered the rules for how to give names to variables in the last video. So it can be like AB1, and then we decide its type. So we have seen that there are two types of floats that we can store basically in Golang. That is float 32 and float 64. So float 32 is a 32-bit floating point number. And for example, let's store inside it the number pi, so 3 to a precision of 2 decimal places. So let us try to use the printf function and print out its type and its value. Yeah, and let's insert IB1 and then AB1. So let's see. As you can see, we got float 32 and then 3.14. So what if we now set it equal to float 64? Oops, okay. Then we get that it is of type float 64. Now, we've covered in the last video, in the previous videos, the concept of type inferring. So we have seen that if we not specifically specify a type for a variable, but we assign it at declaration, then the compiler can deduce on its own the type of the variable. Let's see what happens if we basically declare and initialize a variable AB1 and set it equal to 3 for example, another, we'll say decimal number such as 2.75. Let's see what type will it give. So if we run it, then we get float 64. And this is because actually the default type that Golang will give to a variable by type inferring, in the case of floats, but we will see that this actually applies also to integers. So the amounts of bits that we'll allocate depends also on your computer architecture. So if you have a 64-bit computer, then the default type by type inferring that it will give to a variable of decimal type will be float 64. But if you have a 32-bit computer, then that will be a float 32 variable. You can try on your own and see what kind of computer you're working on at the moment. So with this said, we now know how to declare variables of floating point numbers, so floating point number type. But now let's see other types of integer variables, because so far we've only seen variables of the type int. But there's actually many types of many integer types, and let's see all of them now. So the first type that we'll see is int8, and this type represents an 8-bit signed integer. What this means is that the computer for this data type stores 8 bits in memory, allocating 1 bit for sign and 7 bits for the actual number. So the maximum value that this type can assume in absolute value will be equal to 2 to the 7 minus 1. Why? Because, well, with 7 bits we can represent a number of maximum 2 to the 7 minus 1 if you're a little bit comfortable with binary arithmetic. And if you do a calculation in decimal, this would be the 27. However, we can also drop the 1 bit that we allocated for sign, because with this type here, we can also represent negative numbers, meaning that with int8 type, we can also represent, for example, a number such as minus 97 or minus 9. But what if we want to drop the sign, so we only care, for example, about positive numbers, and then we can declare a uint8, which means an unsigned bit, unsigned 8-bit integer. And this, the range here is augmented. In particular, it goes from 0 to 2 to the 8 minus 1, meaning that the maximum value that we can represent is 255, and the minimum value that you can represent is 0. Well, then there are also other sizes for integers. For example, there's a int16, and this is, you can guess it, it's basically a 16-bit signed integer. And there's also, for example, a uint16, and this is just a 16-bit unsigned integer. And now again, if you know binary arithmetic, it would not be too hard to understand that the maximum number that you can represent with a uint16 would be 2 to the 16 minus 1. But you can also only represent positive numbers. Whereas with int16, you can represent also negative numbers, but the maximum number that you can represent is 2 to the 15 minus 1, of course, in this case, in absolute value. Then there's also the int32 type, which is a 32-bit signed integer. And again, here the maximum value in absolute value is equal to 2 to the 31 minus 1. And then there's also its unsigned counterpart, which is int 32, which is again a 32-bit unsigned integer. And the maximum value that you can represent with it is a 2 to the 32 minus 1, but it's only positive values. And then lastly, we have int 64 and uint 64. And here the range of values with uint 64 is basically 0, 2 to the 64 minus 1. Whereas with int 64, the range of values is minus 2 to the 63 minus 1 up to 2 to the 63 minus 1. And so these are all the main integer types. So then you might say, well, but where does int fit in here? Well, int just depends on your computer architecture. It might be int 32 or int 64, depending on the size of your registers. The registers it's just a type of memory inside your CPU, but that is very fast to access. And so this determines your architecture, whether it's 64 bits or 32 bits. Then there's also another type that is uint, which just like int defaults to uint 32 or uint 64, depending on your computer architecture. Then there's also another important names for these variables, and that might come in handy specifically maybe if you come from Java. And the first one is byte, and byte is basically equal to uint 8, whereas the keyword rune is exactly equal to int 32. So if you declare a variable with the keyword byte, basically it's the same as declaring it with the keyword uint 8. So with this said, we have now seen at many types of integer types. And now that we know how to declare integer variables, let's see how to combine them via operators, arithmetic operators. And there are 5 main ones. The first one is addition, and we use the symbol plus for it. Then there's subtraction, and we use the symbol minus. Then there's multiplication, and we use the symbol star. Then there's division, and we use the slash symbol. And then there's remainder, or also reduction to congruous modulo n, and we use the percentage sign. So let's see how we can use these types. So for example, let's declare an int 16 variable. So var a int 16, and let's set it equal to 400. Then let's declare another variable b, again of int 16 type, equal to 561. So now let's print out with println their difference, and let's see what happens. So, and we get minus 161, which is precisely the difference. And you can see that you can do the same pretty easily with the plus instead of the minus. And by running, you get their sum pretty trivially. But let's now see what happens if one of the numbers is of a different type. So for example, let's declare one with int 32, and the other let's keep it in 64 and 16. Let's see what happens. And as you can see, we get an error because we are summing numbers with different type. Now let's try and also see multiplication. So let's now convert both of them to int 32. Let's set this equal to, for example, 3, and then let's print out their product. And as you can see, this yields their product. And lastly, let's also see at division. But for division, I'm going to show you something. Look at this. We get an integer. And what does that mean? Because if you try to divide, for example, 400 by 3, then you get that this is not actually 133, but it's 133 point something. And well, then what is happening? And here, this is actually, if you come from C, you're already familiar with this concept. If not, then I'll explain it briefly. But here, the division operator in Golang does not represent actual division, but it represents integer division. That means that it returns the quotient between two integers. If you know the log division algorithm, also known as the Euclidean algorithm, when you divide two integers, you basically, so for example, an integer b by an integer a, then you basically find integers values q and r such that you can write b as a times q plus r. Basically, by performing integer division, that is b divided by a, you're returning the value q. And basically, the value q that we got is precisely the quotient between the integer division between b and a. Because if you have b, between a and b. If you have a, for example, 400, you can precisely write 400 as 3 times 133, which you can verify is 399, and then you add 1. So 1 is the remainder. And to get the remainder, we use the operator percentage that we defined above. So if we in fact print out a percentage b, now let's see what we get. Oh yeah, sorry, I forgot to comment those lines out. I don't know why, but okay. So with this set, okay, and as you can see, we get 133 and 1, as expected. So with this set, we have seen the most important arithmetic operations for integers. But what about floats? So with floats, you can add numbers in exactly the same way, as well as subtract them and multiply them. So if we, for example, declare a variable pi of type float64 equal to 3.14, and then another variable, for example, a, again float64 type, equals to -5, then if we print out with print ln pi times a, we exactly get their product. But as you can see, and as I also said before, you might see these kind of anomalies. You could see these weird 0, 0, 0, zeros and then a 1. That's because, again, that's a problem with the floating point number representation in memory in your computer. That's precisely because this 14 here cannot be, when we basically multiply by 2, if you remember that algorithm procedure that we did, cannot be basically reduced to 1 at a certain point by multiplying iteratively by 2. If you, in fact, for example, if you place 25 instead of 14, let's see what happens. We get -16.25, because this number can actually be represented with a finite number of bits inside memory. That the same cannot be said for 14. And this is why 14 gave that weird number and whatever. So, and then between floats, there's actually also division. And division yields the result that you want to see. In fact, this gives -0.65. And so, with this said, I think we have said enough about arithmetic operations and integer types as well as floating point number. And for this reason, I will conclude this video here. And today we're going to look at another very important concept, and that is the concept of constants. So, as the word probably already suggests, a constant in Golang is just a value that doesn't change throughout the program. But let's be a little bit more strict about it, because we could as well just declare a variable, a, for example, of integer type equal to 5, and just not change it throughout the program. Does it count as a constant? Well, from a functional point of view, it could be, but a constant is a type of variable that has fixed value, and that the compiler enforces this particular property of the latter. It is not like our responsibility to leave it as a constant. We're actually not allowed to change it. The way to declare a constant is just like we did with variables. So you declare foreign constants with the same exact syntax, but the only thing that changes is that instead of the var keyword, so the syntax is, instead of the var keyword, you just use const. So for example, to declare a constant of a number type, maybe for example a constant of integer type, and that could be like a number of, so imagine you're like writing some application that has to do with something like a booking of something, the number of seats, and then we can say integer type and set it equal to 25, for example. Okay, also notice another thing that is just a convention. It's not, you're not forced to do that, but often like constants are named with all uppercase. So this is why also in this case we name this constant using only capital letters. And also, just like we did with variables, we can also use type inference with constants. In fact, we can declare a constant, for example, a constant a equal to value, and not specify its type. And the compiler will basically figure out the type on its own without us actually explicitly telling him. So now let's try to write to the console using print line. Let's print out all these constants, so a and pi. Now let's see what happens. And we get all of them out. So now let's also see their types, so that we can see how type inference also works for constants. Now let's see. And we get int float64 as expected. So okay, and as we said above, we actually are not able to reassign a new value to one of these constants. Because let's try to, for example, give a another value. So let's try maybe to change the value of a, and let's see what happens. And in fact, we get an error. Cannot assign to a untyped int constant 55. That's because we declared it as a constant, and thus throughout the program, every time we try to reassign a value to it, we will run into an error. So with this said, we are done with this video, and in the next one we will see getting user input in the terminal. So in other words, getting input from the users from the terminal. Okay. So how can we do that? Well, first of all, we will have, for the first time in this video series, we will have to import some other packages. And these packages that we will need are the following. So just where you have the import statement up there, just include other than thumped, also include bufio and os. So we will need these two other packages. And we will use these two other packages to get user input via a scanner. So to set up a scanner, which means basically something that will read input from the user from the terminal, we will need to, it might look maybe a little intimidating in the eyes of a beginner, because we will need a little more lines of code than maybe you're used to at this point, but don't worry, because I'm sure all these lines of code will actually make sense. So first of all, we need to create a scanner object, and this scanner object is basically responsible for scanning the input of the user. So we can call it maybe scan, and then this scanner object, actually scanner, maybe it's more readable like this, and then let's we basically gonna create an instance of a scanner by writing bufio.newScanner, and then inside of the new scanner we're gonna put in os.stdin, which stands for standard input. So we're gonna create a scanner, an instance of a scanner, and specifying that we're basically passing in standard input. So maybe some of these words might not make sense to you yet, so for example, such as stdin, but maybe if you come from, for example, from C or from other languages, maybe you already understand what these words of course mean. Well, the second thing that we need to do is actually perform a scan operation, meaning that now we want to read what the user will write in the console, and we're going to do this via the scan method. So we're going to say scanner.scan. And once we have done this, we can actually now read the user input. So I'm going to say user input, and then we're going to set it equal to scanner.text. And now we can, for example, test what we did and print out the user input that we got with this scanner. So let's try and run it. So for example, if we for example write hello world, we will get hello world back. So actually, let's just change a little things. For example, let's remove the space here. Let's add a new line just to make it a little bit more pleasant looking. And well, at this point we see that this user input scanner actually works, so we're able to get input from the user and elaborate it in our program. But as we saw, also because I included this %s here, the type of data that we got was a string, because as I mentioned also in the first video, the data that gets exchanged between the user and the program inside the terminal is of course strings. So when we get data from the user, we're getting a string. Okay, but what about, for example, sometimes we might want to have someone input some values which are not strings, but maybe, for example, they're integers. One example of this could be maybe through writing a calculator application where we want to get a number of numbers and then sum them, or for example, multiply them. And then we would not want to have a string, of course, because we want to apply to these values the arithmetic operations that we saw in the 6th video. So how can we do this? In order to do this, we're going to need another package, and this is the strcomp package. And as the name suggests, this package is responsible for typecasting, also known as type conversion. In particular, it implements conversion to and from string representations of data types. So for example, if we have a data type that is in a string format and we want to convert it to an integer, we can do it with this library. And this is specifically what we wanted to do in the example that I made above of a calculator application. So we get an input that is a string and we want to convert it into an integer. So at this point, the first function that we're going to look at is the parseInt function. actually going to look at a couple of functions, and this is the parseInt function alongside the parseUint function. And you might remember that in the video where we talked about arithmetic operations, we also talked about the difference between integers and unsigned integers, uint and int in short. And well, what these things do is precisely that. So they take a string and then they parse the string into an integer. So for now, let's forget about the input, but let's define two variables of string type. So for example, a, and set it equal to, for example, 5, and another one, and let's set it equal to 8. So then, the way in which we can convert, let's call it a1 and b1, these variables into integers is by using the following function. So first thing is we're gonna refer to the package we included, which is strconv. Then I'm gonna say parseInt with capital first letters in both of the words that comprise the function, and then I'm gonna pass parse three arguments. The first one is the string, in this case a. The second one is the base of the representation. In this case, we want it to be represented in base 10. And then the third argument is the bit size. So let's suppose that we want just a regular 64-bit integer. So let's now do the same for b, and so let's just replace the b's with a's. And now for example, let's sum them and set equals c equal to a1 plus b1. And now let's just print c. Let's see what happens. So go run input.go. All right. Yes, this is another important thing that you have to remember, and that is this parseInt function actually returns two values. So the first one is the actual number. The second one is a possible error. So in this case, we're gonna actually have to insert also the error. So let's call it error 1 and error 2, and let's print them in order to later we'll also see a way to just, you could say, forget about them without making a golang for an error, because we know that in golang, whenever we don't use a for example, let's say 23, okay, and then as you can see, the error gave nil because there was no error, the operation was successful, but we now got our sum because 5 plus 8 is actually 13. So we were able to convert from string to integer. And now we can see that we can do the same, but this time with unsigned integers. So we're going to say parseUint, and let's look at what happens when we do this. So now we get still 13. But we can try, for example, and change the sign of one of these values, and let's see what happens in this case. As you can see, we get parsing -5 invalid syntax. So we got an error. This is why we need to basically decompact the output of the parseUint and parseInt functions, because whenever something goes wrong, it gets passed to the error message that is passed as a second output of the function. But as I mentioned before, there's actually a way to kind of discard these error messages and just get the result of the function. So, and also in the way in which we're going to discard them is by putting just a underscore like this. And by putting an underscore, we're basically kind of ignoring the error value, and in such a way that doesn't throw an error. So let's see what happens. As you can see, we get 31 in the output, and as you can see, it works out because 23 plus 8 is actually 31. So the result checks out. And so these are the first functions that are very important to look at of the strconv library, but there are actually more. And one of the other important functions that we want to see is the parsefloat. So parsefloat function. And the parsefloat function just does the same, but does it with floats. So for example, imagine we have a string, for example, C. Actually, I can't see anything above, so let's call it D. And well, imagine we had a string D equal to 2.54. Well, then to parse the string into a float, we'll just have to say, okay, D1 is equal to strconv.parsefloat, and then we're just gonna pass the string that we want to parse, in this case D, and then the bit size. So we can choose either 64 or 32. This time let's choose 64. And now let's, for example, declare another string that is actually a float of 4.77. Let's convert it to a float, and yes, 64 bits. Let's print out the sum of them, so D1 plus E1, and let's see what happens. Okay, yeah, oh, same problem as before. I forgot to, yeah, the errors here. So now it should work, and as you can see, we get 7.31, which is in fact the sum between the two values that we had. So with this said, I think we have covered enough about all the most important functions of the strconv package and also how to make scanners in Golang. Now let's actually make a practical example of this. So let's suppose, let's write practical example. And that is, let's suppose we want to create a program that asks the user for two integer values, and prints out their sum. So how can we do that? Well, and so first of all, let's actually print an initial message that will welcome the user to the program. So for example, welcome to the addition program. Insert two integers, integer, okay, and we will return their sum. So actually I forgot an L there. Okay, and now we're gonna create our scanner with io.new scanner os.stdin, and then we're gonna scan for the first time, and then call it the first variable input 1, and then say the value that we scanned inside input 1. Actually, let's first say println insert first value, okay, like this. Then what we're gonna do is gonna say then insert second value and scan again, and then set input 2 equal to the new text that we scanned. Once we've done this, we are ready to convert the two values that we get. So we're going to say convert the values that we got from string to integer. And to do this, we use this strconv, basically parse int function. So what we do is we say converted input 1 is going to be equal to, actually, and the error that we're going to ignore, going to be equal to strconv.parseInt, and then we're gonna inside set input 1 10 64, and in the same way we're gonna paste it down there, but we're gonna replace the ones with 2's basically, and in this case 2, I'm gonna set okay this equal to 2, and then in the end we're gonna just print line the converted input 1 plus the converted input 2. So there's sum. So let's see if the program works. And as you can see here, oh actually I should have used, just to make it a little bit better looking, I should have used the print function instead of the println function there. So what I'm going to do is, okay, and so let's substitute println with print, and now let's see if the program looks better. Okay, so as you can see, it's your true value, for example, 22 and then 33, and we'll get 55. So this is an example of a program that takes two values and returns their sum. So now, as an exercise, you can try and write a program. So exercise. So the first one will be write a program that takes three values and returns their product, three integer values. So that you're going to use the parse int. The second one is write a program that takes three floats, actually let's say two floats, and returns their sum. And the third program that you can try is write a program that takes a name as an input and then prints out hello name to the console. So with this said, I think we also said enough about user input, and in the next video we'll start looking at comparison operators as well as logical operators. Today we're going to look at two types of important operators as promised in the last video, and these are comparison operators that, like the name suggests, they're operators used to compare values, so values stored inside variables, but also values in general. And then we will cover also logical operators, that are operators that act on Boolean values. So let's first start with comparison operators. So think about, for example, also mathematics. What kind of comparisons would you do between numbers? So let's start with numbers. Well, for example, you might want to know if two numbers are equal, or if two numbers are not equal. Or on the other hand, for example, you might want to see if two number is greater or number is smaller. So how can you do that? You can do this in Golang via the following operators. So we have 6 important comparison operators in Golang. The first one is the equal to operator, and this is quite important because at the beginning you might get it wrong, but the comparison operator for two numbers being equal is the double equal sign. So this is the operator for equal to. And well, why? So sometimes some people just might write only just one equal, but notice that this in Golang is an assignment operator. It is not an operator for comparison. So keep this in mind. Then the second operator is the not equal to, and is represented with an exclamation mark and then a equal sign. And so this is basically not equal to. Sometimes not equal to is also called unequal to. Then the third operator that we need to keep in mind is the less than operator, and this is just your regular less than operator. And this is the greater than operator. And then you have the greater than and a small less than or equal to operators, which are still very important. So the less than or equal to operator is written like this, and so let's write it less than or equal to. Whereas the greater or equal to is written like this, greater or equal. So with this said, we now have the 6 comparison operators that we will treat in this video. Now let's make some examples with them. So also notice that when we compare two numbers, meaning that we have, for example, a number A and a number B, and we compare them with one of these comparison operators, then the result is a Boolean value, because of course when we compare two numbers, we basically say, okay, is this number greater than or equal to this number? So it can be either true or false. Or is this number equal to this number? Then it can either be true or false, of course. And so this is the reason why the result of this comparison is a Boolean value. So let's start and declare maybe a variable A, let's say equal to 23, and then another variable B equal to 25. Okay, so now let's from println A equals B. So let's print out to the console if A is equal to B. Let's see what happens. Well, as you can see, it gives false. Why? Because B is different than A. But what if we change 23? Then let's see what happens. We get true, because of course 23 is equal to 23, namely is equal to itself. So now let's try to print out, on the other hand, if A is greater than B. And as you can see, this gives false. But if we include the equal sign, meaning that if we check if this is greater than or equal to, then we will get true, because they're actually equal. Now let's increment A. So let's set it equal to 28. Let's see what happens if we run it. As you can see, we get true, because of course it's greater than B. So now let's also check. Let's also use the different operator. So let's see if the equal to operator. And as you can see, this also returns true because they're not equal. So this is a very quick introduction to the comparison operators. So you can also, you actually also can compare string. So if you have a string, for example, that is var a string is equal to hello, and then you have another string b equal to hey, then let's see what happens. You get true. In fact, you can say, well, is this string equal to this other string? But let's try to now change this to hello. So let's change the value to exactly the same one. Let's see what happens. We get false because they're actually equal. Not only can you compare strings like this, so meaning you can check if they're equal, you can also check if a string is greater than another string. And this might be a little confusing maybe to some of you if you haven't, if you're not super familiar with character encodings such as UTF-8 and ASCII and so on. But the reason why some values are bigger than others, or some characters are bigger than others, is because of their position on, so basically their numeric value to which they're mapped. So let's try, for example, and compare A and capital A. So if you run this, you get true. In other words, you get that small a is bigger than capital A, because it comes after capital A in the encoding. And so you can try, but let's try to put B here instead of A. Let's see what happens. We get false because B comes after A. And so this is also how you can compare strings with equal to, not equal to, and less than or equal to, greater than or equal to, and so on. So with this said, we can now move to logical operators that are the following. So the first one is the logical AND, and that is represented by the following symbol. Then we have the logical OR, and that is represented by this symbol here. And then we have the logical NOT, that is represented by this exclamation. And so we might ask, well, how do these operators actually act on Boolean values, and what kind of output do they give us? So if you're familiar with logic, or if you have programmed in another programming language, then you can just straight out skip this part, because it's exactly how they work, for example, in C, or in, I don't know, Java, or in JavaScript. And so you don't need to review them. On the other hand, if you have never programmed before, but maybe you have some background in mathematical logic, especially the beginning, not even mathematical logic, just the introduction that is given to these operators in discrete mathematics, then again, you probably already are familiar with them, and you just need to see how they're applied in programming. These operators are also part of a class of operators that are called true functional connectives. This means that basically, given some input that are Boolean values, then the output only depends on the Boolean values that you give in. So so for this reason, we can build some truth tables for these operators, and truth tables basically just give us a graphical view of what outputs these operators give us for what inputs. So let's start by building a truth table for the operator NOT. So the operator NOT, let's here put maybe true. Let's put false. Actually, let's put this is the input, and then this is the output. So if we compute NOT of true, then we will get false. And if we compute NOT of false, then we get true. In other words, the NOT operator just switches the truth value of the input, meaning that if we say NOT of something that is true, then we get out false. And then if we compute NOT of something that is false, we get true. So we can make an example. For example, let's print ln maybe NOT, and then let's insert here a true statement. For example, let's declare a variable x int equal to 5. Then if we say x is greater than 3, and that is true, but if we negate it, then we run it, we get false, because we have negated a true statement. Now let's try and switch this with a less than sign. Let's see what we get. We should get true because we have negated a false statement. So this is how the not operator works. On the other hand, the OR operator requires two values. So the OR operator basically takes in two Boolean values and gives back another Boolean value. So, and the way in which it does that, it follows basically the following truth value. So I'm going to denote x for the first input, then y for the second input. Actually, let's use a tab to make it more clean. And then I'm going to denote x and x or y for the output. So let's first cover the case where both x and y are true. Well, then x or y is true. This might sound a little counterintuitive, maybe if it's the first time being exposed to these operators, because, well, in ordinary life, when you say this or that, you actually mean an exclusive this or that. You would not accept having both of them. For example, imagine go to the supermarket and buy, for example, apples or oranges. But imagine if the person you said this to would come back with both of them, then you would probably be disappointed. That's because that's another type of operator that's called XOR, or exclusive OR. But the standard OR that we will use, and also in Golang, yields true for x and y equal to true. So now let's suppose that x is true and y is false. Well, then the result of the x or y operator is true. Well, what about x false and y true? Then the result is true again. But the only case in which x or y is false is it's if they're both false. So if they're both false, then the result is false. So now we can try and work a little bit with this operator. So suppose we again have the variable up there x that is equal to 5. So let's now try and print out the Boolean value given by, for example, the expression x equals 5. And remember that in Golang the OR operator is with this symbol here. So x equals to 5 or x equals to 3. So one of them is false because x is not equal to 3, but the other one is true. So let's see what the result is, and that is true. Because again, according to the truth table we gave above, the first Boolean value we passed was true. And so we are in this case here, so where x is true and y is false, and the result is of course true. But now let's try to pass in two false values. So x not equal to 5 and x equals to 3. And as you can see, we get false. So now we can make another example. For example, I don't know, 5 is greater than 0, or 2 is greater than 0. These are both true, and we should get true. As you can see, it's true. So with this said, I think we've said enough about the OR operator, and now we're ready to introduce the last operator of this video, that is the AND operator, also denoted with the symbol here. So let's write a truth value for it. So again, the first input will be denoted with an x, the second input with a y, and the output with a x and y. So the AND operator, on the other hand, returns true if and only if both of them are true. So if x is true and y is true, then the AND operator is true. Let's space it a little bit. But if one of them is false, so if either x is true and y is false, this is false. If x is false and y is true, then this is also false. And also if they're both false, then also the AND operator is also false. So this is just true if both of them are satisfied, and this is why it is often used as a way to check if two conditions are valid at the same time. For example, let's imagine that we want to print out if a number, our x, for example, is greater than 1 and less than 10. So this is an example of a situation where we want to use the AND operator, and we will see that the result is true because our variable satisfies both of these conditions at the same time, because it is equal to 5 and 5 is greater than 1, but it's also less than 10. But now let's see what happens if we say is less than 4 on the other hand, and we will see that this is false because 5 is not less than 4, and so x does not satisfy both of these conditions at once. It only satisfies the first one, but according to the truth value that we gave, this is not sufficient in order to make the AND statement equal to true. And so with this said, we now know how to work with comparison operators and logical operators, and now we're ready to introduce if-else statements in the next video. And because also we will see how we will use these operators extensively when we will work with if-else statements in the last video. So we're now comfortable with the concept of logical operators as well as comparison operators. So let's here, just one sentence. And so now we know how to combine Boolean values together into more complex, we could say, expressions. Actually, we can now call these complex expressions, we're going to refer to them as conditions. So, and we say that a condition is true if this complex expression, that can also be just one Boolean value, is true. Whereas we say that it is false, or that it is not satisfied if evaluating it yields false as a Boolean value. So now that we have that, sometimes in our programs we want to react in a certain way if a certain condition is satisfied or not. So for example, imagine that you have a program where they're going to ask you to compute a factorial. So of course, the classical integer factorial, and here we're ignoring various extrapolations that can be done, does not make sense for example, a negative number, or for a number that is not an integer. And so for this reason, imagine that we make a function to make a factorial, and they pass, for example, a negative integer inside of it. Then we might want, for example, to check if that value is actually positive. And if it's negative, we're going to maybe return an error value. Or for example, imagine that you have a program which checks your name, and maybe if your name starts with an A, there's going to be a message, but you want to be a different message if your name starts with a B. So how can we do this? Actually, this is not realistic at all, but it's just an example. But how can you do this? This is done via if statements. So an if statement in a Golang program basically says, okay, if a, and the general syntax is if condition, then code. And usually the code inside the curly braces is placed in a new line. So let's make an example. Let's make a variable a equal to 5. So let's suppose that we want to write a program that prints equal to 5 if a is equal to 5, and else it says not equal to 5. So to check, so to do this, we're going to say if a is equal to 5, using the operators we introduced in the last video, equals. Well, then we're going to say println a is equal to 5. So let's see. Oops, I think I forgot a quote. Yes, I did. Okay. So let's try and run this. As you can see, we get a is equal to 5. But now, for example, what if instead of 5 we augment it and we put it equal to 8? What happens? Let's see. We get nothing because the line of code didn't run because this condition was not met. So what if statement does is, okay, if this condition here is met, then run the code inside. If not, just skip it. So this is why nothing run. Now let's, for example, for example, suppose that now we want to print another message if a is not equal to 5. So we're gonna say a way could be if a not equal to 5. So we're gonna make another if statement and say, okay, println a is not equal to 5, for example. And so if we now rerun the program, we're gonna see that a is not equal to 5. So actually, in a way, we achieved our goal. But this is not a very elegant way to do it. Why? Well, because the program checks the condition twice. So it basically checks, okay, is a equal to 5? Then it goes here and then say, okay, is a different than 5? Well, in actuality, the program already knows if a is not equal to 5 when it checks if it's equal to 5, trivially. So how can we basically spare this other check? And how can you also write the code in a more compact way? Well, we can use the else keyword. So right after our if statement here, if a is equal to 5, then we can say else, and that meaning if that condition is not satisfied, then we can just print a is not equal to 5. And we will see that the program will have the exact same it will function in the exact same way, as you can see. And this is a better way to write it. So now we have learned how to control the program based on some conditions. So we can basically say, okay, if a condition is true, then do this. And if that condition is not true, so else, we can do that. But now sometimes we want to check multiple conditions. So for example, we want to say a is equal to 5 is a is equal to 5. But maybe we want to say a is negative if it's less than 0, a is positive if it's greater than 0. Then how can we do that? In this case, we will use another keyword, and that is the else if keyword. So it just means, okay, if a is not equal to 5, then if that is not equal to 5, but it might be something else, then run this other line of code. Now we're gonna give the general syntax for that expression, and that is else if, and then after we just put our condition. So in this case, for example, let's say else if a is less than 0. Then if a is less than 0, we want to print out a is less than 0. And then we can say else if a is greater than 0. Then we can just say a is greater than 0. And maybe lastly, we want to say if a is equal to 0, we want to say a is 0. But in this case, notice that we have already spanned all of the integers because we covered all positive integers, all negative integers. Then here we have a case for 5, and the last case that basically is possible is just 0. So we could say else if a is equal to 0 and then run the code, but we can write it more elegantly as just else, and we can write println a is equal to 0. So let's try to run our code now, and let's see what we get. We get a is greater than 0. Because, of course, 8 is greater than 0. But now, what if, for example, we decrement it, and we set it equal to -4. Let's see what happens. We got a is less than 0, as expected. And now let's try and, for example, augment this value. So maybe to 0. So maybe to 0, let's see what happens. We got a is equal to 0, as expected. So this is basically how else, if else and else if statements work. So it's just a way to control and react in a certain way based on certain conditions. And now another important thing that you might want to know is that, well, inside an if statement you can actually nest other if statements. So you might say, okay, if a is equal to 5, then we might declare another variable that could be b, and we can set it equal to 2 for now. Let's set this equal to 5 again. So inside the case for which a is equal to 5, we can actually nest another if statement. So we're going to say if, for example, b is equal to 2, then we're going to let's remove this line here. We're going to print out thumbed print line a is equal to 5 and b is equal to 2. And we can also include an else inside it, and we can say else. We're going to just say a is equal to 5. So let's see what happens here. If we run it, we get a is equal to 5 and b is equal to 2, because basically what happened with nested if statements, what happens is, okay, we go inside the first if statement, then as usual this condition, for example, is true, so as a Boolean value this expression is true, and then we go inside because that is true. If it was not true, we would have skipped it, but since it's true, we are now inside here, and here we're confronted with another if statement, if else block basically, and now we check if this condition is true. Since this condition is true because b is equal to 2, then we go inside here, and this is what we print. If b was not true, for example, if it was equal to 6, for example, then we will not execute this code and we would go inside the else block. In fact, let's see what happens if that is the case and we get a is equal to 5 and nothing else, because of course b was not equal to 2, and so we have skipped this else statement. So with this said, you now know how to write if else blocks, and also use if else and else if inside Golang, and you also know how to write nested if statements. In the next video, we're going to see another way to react based on some conditions inside a Golang program, and that is using what is known as switch statements. Hello everyone, and welcome to this new video about Golang. And today we're going to look at switch statements. So switch statements are an alternative way to basically handle a program in different ways according to a condition. So basically checking for a condition and reacting accordingly. So in the last video we've seen if-else statements, and you might ask, well, isn't if-else statements enough? Well, technically you could use if-else statements everywhere and just forget about switch statements, but sometimes switch statements are better for a variety of reasons. That can be not only readability, because of course switch statements, when you have to check just one variable in various cases of it, it can make the code way more readable, but it also can improve performances. So if you worked with C, or for example with C++ or Java, then you're already familiar with switch statements. But however, you need to be careful about one thing. That is, for example, in C, you're probably, and forget about this if you never used C, but I'm going to introduce at the beginning because I'm sure you will make this error quite often if you come from C. And that is, in C, you always break the statement after, because otherwise you're going to run the other cases. So in Golang, you do not need to do this. It basically will just execute just one case on its own. So you will not need to put a break statement in switch expressions. So let's start with now explaining what a switch expression is. So now let's suppose we want to write a program that takes a number between 0 to 9 in integer format and then returns extended basically English word for that number. So for example, you might have 0 and then you get as an output the string 0, 1, and then you get 1, and so on. Well, imagine doing that with if-else statements. So imagine you will have a value here, type integer and equal, for example, 5. Then what you have to do is if value is equal to 0, then print, I don't know, it would be like font print line 0. And then you will basically copy this and then say, oops, else if value equals to 1, then print out 1. And then else if value equals 2, and so on. And so you can see this is not clean at all, and also it's not super good in terms of performances. So how can we also optimize this? Well, we can use a switch statement. And the syntax for a switch statement is basically the following. It will be switch, then the variable we're going to check, and then we're gonna put some curly braces. Actually, let's make a multi-line comment for it, because like this. And then inside the curly braces, we're gonna put the actual logic code. And so, for example, we're gonna put case, and then the value for that case, then a colon, and the code we want to execute for that case. So case value 2, for example, and then code, and so on. Sometimes, however, you want to also insert a default case. So basically, that means, okay, if it's neither, then if it basically doesn't fit, if it doesn't fit in one of these cases, then you might just want to return a default clause, and then just return a value for. And this is why it's called a default statement. And where we're not sure that a value will be in one of these cases, it's important that we include one, because otherwise maybe we might break our program. So with this said, let's now actually use it practically. So let's switch on the value of value. So switch value, and then we're going to open curly braces, and here we're going to include value cases for value. So maybe what we might include case 0, and I'm going to say font print line 0, then case 1, and then font print line, and then 1. And then you can repeat this, and as you can see, oh, I forgot the quote. Okay, and as you can see, this is very simple. So for this reason, and this is way cleaner. So let's copy paste this, and okay, so I think we're done. Yes, because we have, okay, yeah, 10 cases, and now we just need to basically change the value for each case, and that is, in this case it's 3, and here it's 4, and here's 5, it's 6, here's 7, here's 8, and here's 9. And also we need to change the values inside. So this is going to be 9, and this one. And so this is how we can actually do the same thing as before, but using a switch statement. And then maybe we want to insert a default clause. So maybe if our value is nothing, is not between 0 and 1, we can say a value exceeds range 0 to 9, for example. And this is basically our check. So now let's try to run this code. Go run switch.go. Then we get 5 because our variable is equal to 5. Now let's try to put in 1, for example, and we get 1. And so instead, if we, for example, increase our variable by a lot, maybe put it equal to 16, then if we try to run it, we will get value exceeds range 0.9. And so this is basically how you work with switch statements. So with this said, I think we have covered enough in this video, and in the next one we're going to start looking at another important data type in Golang, and that is arrays. Language. Today we're going to look at arrays. So arrays are one of the most important data structures that we will see in Golang, and so let's start by talking about what an array is. So an array is just, for functionally speaking, a collection of elements of the same type. But be careful that, especially maybe if you come from other languages, for example, especially new high-level dynamically typed languages and scripting languages like, I don't know, Ruby, Python, JavaScript. But if you don't know these languages, don't worry. But if you don't come from these languages, then I want to, I want to place more emphasis on the fact that an array in Golang is a collection of elements at the same time of fixed size. This means that once we declare it, so once we declare a collection of elements of a certain size, for example, 6 elements of a determinate type, then we won't be able to add new elements to this array. So, for example, imagine that you have an array of 3 elements, okay, 301, 401, 501. Then if I want to add 601 to this array, but I initialized it to be an array of 3 int elements, then I won't be able to do that. And in the next video, we will see how we can do that using another data structure, and that is slices. So, we need slices to dynamically increase the size. And if you come from C, and again, if you don't know C, don't worry about what I'm saying right now, you can think of arrays as just standard C arrays, and slices as basically calocate, malocate, basically arrays where you're allocating memory dynamically on the heap. So this is how you can think that if you come from C. So let's first see how we can just declare an array and not initialize it. So to declare an array, we can use the var keyword, as we saw also in the previous videos, and then the general syntax is var, as we said here. Then we're gonna have the identifier, so the name of the array. So we can call array1, for example, and then we're going to put the number of elements in square braces. So basically the general syntax would be number of elements in square braces and then the type. So suppose that we want to define an array of 4 strings, then the way we would do that is square braces, the number of elements, 4, and then string. And so this is how we can declare an array. Now, also another important thing that you have to know is that if we declare an array and we don't put anything inside it, so we do not specify any of its elements, then Golang by default sets it equal to an empty array. So we can try and print this array out and see what happens. As you can see, we get the empty array out. Also, as you can see in Golang, you can print out arrays directly like this, and it will just print the elements. So now that we've seen how we can declare arrays, let's also see how we can declare and initialize arrays. So to declare and initialize an array, we can do it, of course, as we've also seen in other videos. When we declare and initialize a variable, we can also use type inference, meaning that we can also declare an array using this operator here. Let's first see how we can do it by specifying the type without type inference, and so how to declare it and initialize it using the var keyword. So again, let's say we want to define an array 2 that is a collection of 5 strings, and so let's say 5 string, and then we want to initialize it to, for example, hi, hey, hello, and some other random strings. So in order to do that, we're gonna write on the left like this, var array2 and the collection of 5 strings, and then we're gonna put an equal sign. Then we're gonna put again 5 slots, so with square braces, and then type of the array, which is gonna be a string, and then with curly braces, we're gonna start to list the elements of the array like this. And so, for example, I'm gonna put here hey, then hello, English, Chinese, Mandarin Chinese, and Arabic. Okay, so this is basically an example of an initialization and declaration of an array at the same time. So now if we try and print out, actually to not throw an error, we need to print both of them out. So if we print the array out, as you can see, we get all the elements. Okay, so now that we have defined an array, basically all these strings, which we will see then in Golang, a string is also a slice. Actually, we have to. Okay, let's not talk about it yet. But basically, for now, don't worry about it. Let's just give a very high-level view. But basically, the strings that are inside are placed one next to each other in memory base. So now that we have an array, we also can not only just access the whole array and print out all of its elements, we can also print just one element out by accessing a specific element inside of it. And we do this by basically just assigning a number to each element, starting from the first one. So we start to count basically, but it's important that you know that we start to count from 0. And if you come from any other programming language, I'm sure you're already used to it, unless you come from Pascal, for example. But basically, if you've never programmed before, or maybe come from Pascal, then just know that we start to count from 0, meaning that the hey string is at place 0 inside this array, then the hello is at place 1, English is at place 2, and the other strings are at place 3 and 4 respectively. So, for example, imagine that, let's just make another array of numbers. Maybe let's set it equal to array 3, then let's let it be a array of 5 integers. Then we can put 1, 22, 44, 55, minus 32. Imagine that we want to print out 44. Then what we will do will be from the print line, and then we would say array 3, and then with square braces we will access the third element, which is basically 2. So by starting to count from 0. And so if we run this, actually let's comment out this thing here. So if we run this, we get 44, which is the third element, but it's on the second index. And for example, if we want to print 55 out, then we will just increase it by 1 and get 3, and let's see what we get. We get 55, as you can see. So this is basically how you can print out single elements of an array, accessing them by their index, basically. As we mentioned earlier too, we can also declare and initialize an array using the definition operator, :equals, or just var equals without the type. For example, we can redeclare and initialize our array tree array by saying R3 is just equal to, I forgot how many elements were there, but let's suppose it was 4 elements, integer type, then 11, 33, then -2 and -5, okay, something like that. Or you can also declare and initialize it with the colon equals operator, like this. And so both will work. For example, if you try to comment this out and just leave the other one, then if you run it, we get -5 in this case because we printed out the element array position 3, which is the 4th element. And again, if we on the other hand we remove the comment here and we place it on the other line, we see that it still works. So we get also define array in this way. And another thing that you should know is that just like with types, when we declare and initialize at the same time a variable with the colon equal operator or with bar equals without specifying the type, we infer the type. We can also infer the number of elements, and the compiler can tell it from the initialized value. How can we do that? We will put 3 dots inside the square braces like this, and in this way, as you can see, it will work. The array will have size 4. That is the size of the elements we placed inside the initialized array. For example, if we add another element, it will still work, and it will have size 5. So this is another way to declare and initialize arrays, and where we will infer the length of the array and also the type by declaring it like this. And also notice that if you want to print the length of an array, you can just use the LAN method like this, and as you can see, it will print out the length of the array, which in this case is 5. And the last thing that we need to see in this video is how to declare multidimensional arrays, because sometimes we might want to work with data that can be represented with a matrix. So how can we represent a matrix in Golang? Well, a matrix in Golang can be just represented by a 2-dimensional array like this. And to declare the 2-dimensional array, we can just say a var, as before. Let's use the colon equal operator, and then we can say the number of rows in this case, then the number of columns. For example, let's say that we want to declare a 3x3 matrix. Then we will just specify numbers of rows and columns in square braces like this, and then we will specify the type. And then we will let's now initialize and declare it at the same time, and we will now include the arrays. And a 2-dimensional array, and this also holds for 3-dimensional and general n-dimensional arrays, is just an array of arrays. And so in this case, this is just an array of 3 arrays of 3 elements. And an example of this can be 1, 2, 3, then the array 4, 5, 6, and then the array 7, 8, 9. This is a valid 3x3 matrix. And if we try to print it out, we can see that we get the following array of arrays, also known as a 2-dimensional array, also known as a matrix. So with this said, I think we've said enough, and in the next video we'll introduce the other important notion of slices in the last video. So we have seen what arrays are, and so we have seen that arrays are basically collections of elements of the same type, and these elements of the same type are basically stored contiguously in memory. This means that each basically memory cell that stores a value, the next one will be the next value of the array, so they will be stored one next to each other in memory. But now we're interested in slices. Why? Well, because in the last video we've seen that arrays are actually static in size, meaning that when we declare an array, for example R, an array of 3 integers, well then we cannot add any more elements. The array that we declared is an array of 3 integers, and that's it. There's no way to increase the size of this array dynamically. That's why in a lot of cases, and if you've come maybe from some other language, maybe a more high-level abstracted language like, I don't know, JavaScript or Python, you might use collections of data that naturally, without you worrying about anything, already grow in size. Or maybe if you come from a language with no garbage collection and where you actually have to do the memory management yourself, like in C, then you might be used to using, you know, these functions like malloc, calloc. Well, here in Golang takes care of the allocation, dynamic allocation of memory. But instead of using arrays, we will have to use slices. So if you come from C, again, you can think of slices as just, you know, calloced or /malloced arrays, where then each time we add a new element, we basically reallocate them to store more elements, and then we add a new element at the top. But if you do not come from C, then do not worry about it. And slices are basically just arrays that grow dynamically in size, meaning that slices are just like arrays, collection of elements of the same type. But if we want to add new elements, we can do that basically. And so let's start by seeing how we can declare a slice. So to declare a slice, we using the var keyword and just declare it without initializing it, we just use var, then we call, for example, slice1, and then we use, as before, the square brackets, but this time we write nothing in them. And basically we don't specify its size. By doing this, basically we're telling the compiler this is not an array, because I'm not telling you a specified size. This is a slice. So let's try to print out to the console the slice we created. As you can see, we get an empty slice. In fact, golang, just like with other data types, because now you should know that basically if you just initialize a boolean value and you print it out, meaning that it has no value, then golang automatically sets equal to false. As well as for integers, the automatic value gets set to is 0. In this case, arrays and slices will just get set to an empty array or slice respectively. And now see how to declare a slice. But what about initializing it? So what if we want to also tell the compiler what we want to set it equal to? And well, to do that, we can do it in many ways. One way is to use slice literal syntax. And just like with arrays, we can basically just write the square braces again, then string, and then inside of here we can write the elements. For example, we want to say, I don't know, like hello, then how are you, maybe. And then we can now try to print again. Let's see what we get. We get the following slice printed out to the console. As you can see also, by printing slices to the console in Golang, you just get out the these curly braces with inside the elements of the slice. You can also create slices from an array, and this is called array slicing. So we're gonna do it up here, creating slices from array via slicing. So let's declare an array, and also notice that here, just like with other data types, you can just basically type in for your variable using the, as you can see, this colon equal operators, and as you can see, this will work again because it just inferred the type. So just the compiler deduced from the right hand side that slice1 is a slice data type. And also now let's go and see how we can create slices from arrays. So let's first declare an array, maybe an array of 3 integers, actually 5 integers. Let's make it a little bit bigger, and let's set it equal to the following, for example. So 10, 20, 30, 40, and 50. Well, let's now set slice equal to array, and to create a slice from an array, by slicing an array, we basically need to slice the array starting from an index and ending to an index. In the following way, we will basically say slice colon equals the name of our array. Actually, here is the name of our slice, just to specify, maybe to be more precise. And then we need to specify here the start index. And notice that in our slicing we will include the start index inside the new slice we will create, and then the end index. So in this case, suppose that we want to create a slice containing 10, 20, and 30. Well, to do that, we will basically just do array 0 going up to 3. Why? Because the end index will not be included. So we need to specify one index after it. And when we will do that, let's try and actually let's print slice1 slice instead of slice1. Let's see what happens. As you can see, we get 10, 20, and 30. But what we got here is not a it's not an array; it is a slice. So we can try to convince ourselves of this by printing out the type of the slice variable. Let's see what we get. As you can see, we get a slice of integers. And so this should convince you that this is a slice. And so this is another way of creating slices. Now notice that we wanted to basically get an array containing 10, 20, and 30. So basically starts from the beginning. Well, in these cases, we can just omit the starting index. And as you can see, the code will still work. And because basically if we omit the starting index, it just means start from 0. in the same way, if we want to create an array starting from the index 2 up to the end, we can just omit the last index, and we will get all the elements after it, as you can see. So these are some other, you could say, notational things that you should know about array slicing to create slices. And now we're going to see a last way to create a slice, and that is using the make function. So actually, let's delete these lines of code here. And so by creating, so with the make function actually. So how can we do that? Well, we will just create the name of the variable. In this case, maybe let's call it s1, or actually slice1. It will be actually just slice. Then we will use the colon equals operator to make a type infer from the right hand side. You could just declare a slice, but it might be a little bit more time consuming, so we're just gonna stick with this. And then we're gonna use make, and then inside of here we will specify that we want a slice, for example, of integers. It could be as well of strings, of Boolean values, whatever you want. Let's do integers here for an example, and then we will specify the length of the slice. Notice that here, of course, the length is not fixed, meaning that if we add new elements, we will see how we can add new elements to a slice. We can increase the length. Let's see, set it equal to 7, for example. Now, let's printing out the slice is again not initialized. It will print out a slice of zeros. In fact, we can try that. As you can see, we will get all zeros. And I'll show you something. I'll show that just like we did with arrays, that we can access and change the values at certain indexes, and also we start to count from 0. Remember about that. Also here we can do that, and in fact we can just for example, let's just add some elements to it. So like this. Oops. Okay. And then here too, and let's see, and now let's try to print it out. As you can see, we get our slice with the elements we added. So, but there's one difference. Now, instead of what we've seen with arrays, that basically the length of the array was static, here we can add new elements. How can we do that? We will use the append function. And so, notice that the append function will not change the slice we have, but rather it will just return a new slice with a new value at the end. So how can we, so in order to basically change our array, we need to reassign it to the append function of the slice. So imagine that we want to add, and notice that with the append function, we can add as many elements as we want. So how can we do that? We will just specify as the first argument the slice to which we want to append the values. And now suppose we want to append 8, 9, and 10 to complete basically our counting of numbers up to 10. Then we will just specify the values that we want to add. And now let's try to print the slice out. As you can see, we get 1, 2, 3 up to 10. So this is how you use the append function. This is basically how you can add new elements to a slice. Now that we've seen this, we now need to specify some more things about slices, and these are the length and the capacity. So you're probably already familiar with the concept of length of an array. But also slices, of course, can have a length. But with slices being dynamically allocated, they also have a concept of capacity. And in short, a very high-level view of both of these things is that the length of a slice is the number of elements inside of it, whereas the capacity, also used with the cap function, is basically the memory capacity. So the values it can potentially store. So let's try to print both of these out in the console. So, example, length on slice and then cap on slice, and let's see what we get. As you can see, we get 10 and 14. That's because 10 is the length. As you can see, our slice contains 10 elements, but the capacity is 14, meaning that the total number of integer values that this slice can store as of now is 14. Now let's try to add other values. Let's see how the capacity also changes. So for example, let's add 11, 12, 13, 14, for example. And let's see now. Oh, sorry, let's add another one. I forgot to. I should have added also 15. As you can see, the capacity raises. And now we have 16 as capacity. But the length, again, is just the number of elements that we have. And as you can see in this case, now it became 15. Well, now that we have seen how to declare slices, initialize slices, work with them, change elements inside of them, append new values, and all these things. Let's now focus on something else, and that is how can we compare slices, because we have seen that in Golang you can compare data types. You can compare Boolean values, you can compare integers. You can say 10 is if you say, for example, 10 is equal to 23, this will yield false. 10 is equal to 10, this will yield true. You can say 10 is bigger than 23. So how can we also compare slices? For example, how can we say that two slices are equal? Because ideally, intuitively, you would say that this slice here should be equal to another slice like this. But in Golang, you cannot just directly have, for example, a slice and say that it's equal to slice 1. In fact, let's actually try to do that and convince yourself that that is the case. For example, let's declare slice 1. This time let's do strings, and just to change a little bit. So string, and let's, for example, hello, hi. And then slice 2, let's say set it equal to, I don't know, hello, hola. Maybe salut. So let's now, oops, I forgot to print the condition out. Now let's try, for example, to print out slice 1 equals slice 2. Let's see what the Go compiler will tell us. As you can see, the Go compiler will throw an error. It will say embedded operation slice 1 equals slice 2. Slice can only be compared to nil. What this means is that you can use the direct comparison operator just to check if a slice is nil, meaning that if it's basically null in other languages, you would say. So how can we actually compare slices between each other and get actually interesting results, meaning that basically have a way to check if all the elements inside of slice are the same? And well, so in order to do this, we will use the slices package. And notice, and this is very important, that in order to use this package, you will have to have at least the newest Go version, that is Go 1.21.4. If not, I will show another way to compare slices in Golang without the slices package, because you can actually use another package that's called reflect to do the same thing. But now let's see how we can first use the slices package. And in the slices package, you have this function which is called equal, and so we can use this equal as follows. So we will print it. The syntax is the following. First of all, we will see slices, which is the package to which the equal function is located in. Then we will say equal, and then we will pass in the two slices that we want to compare. In this case, slice 1 and slice 2. Let's see what we get as a output, and we get false. Why? Because these slices are not the same. But now let's try and print out slices.equal slice 1 and then the following slice. So hello and then hi, for example. Let's see what we get. Oops. Oh, I forgot something. Let's see. Oh yeah, I forgot a brace at the end. As you can see, we get true because the two slices are actually equal, as you can see. And this package also has a lot of other really useful functions that you can use when working with slices. For example, let's declare a new slice, this time of integers maybe, and let's set it equal maybe to 11, 22, then 55, then 66, then 77. Then you can have a function in the slices package to determine where is the first occurrence of an element, and this is the index function. So, and the way in which you use it is just by saying slices. Slices.index, then you basically insert the slice variable that you want to check. Then you insert the slice that over which you want to find the element, and then you insert the value. So for example, let's say that we want to find the first occurrence, the first index occurrence of the value 55. Let's print it out to the console. As you can see, we get 2 because 55 is located at the first time at the position 2, index 2. Of course, you need to remember that we start counting from 0. Not only that, but the slices package also has a function called insert to insert a value inside the slice at a specific index. And the way in which we do that is the following. So, of course, here notice that just like with the append function, you need to reassign the variable to the value that you're basically getting as a return, as an output from the insert function. And actually slice is equal to slices.insert. Then here you will put the slice to which you want to insert the value. Then you will put the index at which you want to insert it. So let's suppose that we want to insert at position 2 the value 33 because it's actually missing. So 33 and 44 are missing. So we will just put position 2. Then we will insert the value that the values that we want to insert. In this case, let's put 33 and 44 because here you can insert as many values as you want. It will just tell you from which position you will start inserting them. So now let's try to print out again the slice. Let's see what we get. As you can see, we get the slice of multiples of 11 up to 77, as expected. Also, another interesting function of the slices package is the isSorted function. In fact, you can print out if a slice is sorted. Actually, a slice is not sorted. Let's try to print out our slice variable. Let's see what we get. We should get true because it is sorted. But now let's try to insert a value that is, for example, I don't know, 55 here again. You get that it's not sorted. In fact, you get false. So this is basically, these are the most important functions of the slices package. You can check all the other ones in the documentation. You can just look it up on the Go documentation. There's actually also other functions that allow you to sort slices. There's functions that allow you to search for values using binary search on sorted slices. But in this video, we're just seeing the basics. And you can look these other things up on the documentation, and it's really well written, so you will understand it. So now, as promised, we will see another way to compare slices without the newest Go version, and that is using the reflect package. So let's again declare a slice, example of integers. We won't be fancy this time, just 1, 2, 3, 4. Now, if we try to print out reflect dot deep equal, then slice, and then for example another slice of integers, 2, 3, 4. Let's see. A brace. So as you can see, we get true because the two are equal. Now if we try and, for example, change it, maybe we increase this value, we get false because they're not true. And so this is how you compare slices using both the slices package and the reflect package. And now as a last thing, we will see how slices work when reassigning them to other values and changing the values we assigned them to. So one of the important things that you have to keep in mind is that slices, when you have a slice variable, so for example slice equals a slice of integers, 1, 4, minus 3, 5, for example, well then this slice variable will behave, we could say, in a weird way when we reassign it to another variable. So let's create another slice variable, a slice of integers, and let's call it slice 2, and then let's set slice 2 equal to slice. Now let's try to change slice 2 at an index, for example, and let's set the first element to 55. Now let's try to print out slice 1. So slice, the original variable. Let's see what we have. As you can see, we also modified the initial value. And so this is rather bizarre. Maybe if you have never programmed before, you say, why did we modify this original value if we set it equal to, if we basically just assign the value of this to another variable? We should have just modified slice 2. Well, the reason why this happens is because slice is a reference type, we could say, or more precisely, slice is actually a pointer to a location in memory. Being a pointer to a location in memory, in particular to the first one, okay, so to this one in memory, then when we assign it to another variable, we're actually assigning to this other variable the same position in memory. So when we modify that, we then also modify this. So in order to store inside of slice 2 the values of the slice, we need to use another function. And this is the function copy. So instead of saying slice 2 is equal to slice, we will say, so let's remove the lines above. Then in order to do that, first of all, we need to use the make function to redeclare the slice 2 slice variable. We will use the make function, set it equal to a slice of integers of length equal to the length of the first slice. Then it will copy the content of slice inside slice 2. So actually you need to put the destination first and then the source. And now let's try to modify slice 2 to the first index, for example, set it equal to 55 again as before. Let's see what happens. As you can see, the values of the first slice are not changed, but the values of the second slice, which are all equal to slice, were then changed. The first one got set up to 55 and the other one remained the same. So the behavior of slices with respect to this, we could say, reassignment is very different from the behavior of arrays. So as an exercise, you can try and create an array and then assign the value of that array to a new variable. And once you have done that, then change the new variable and print both of them out. So you will see that basically the new variable that we have created, changing that will not change the original array. This is because when you reassign the value of this new array to the value of the old array, the value of the original array actually just got copied inside the new array. In contrary to what happens with slices, where you actually save the position in memory of the first element. So with this said, I think we have said enough in this video, and in the next one we will look at for loops. Well, why did I say for loops? That's because in Golang there's actually no other loops other than for. So there's no while loops, there's no do while loops if you come from other languages. You might be familiar with this concept, but here in Golang there's just a for loop and you use it to do all loops. So we will start by looking at the classical for loop. So first of all, what is a loop? In programming languages, a loop is just a bunch of code that you repeat over and over again until, for example, a certain condition is met. So to initialize a for loop, the syntax is the following. You say for, then we have, actually let's put it in a comment. So the syntax for a for loop is for, then we have what is known as an initialization condition. This is basically what is done when we start the loop. Then we have a condition that each time gets checked. And notice these statements are separated by a semicolon. So we have a condition that each time is checked in order for the loop to be run. So if the condition is satisfied, then we run the loop again. And there's a post condition, which is a bunch of code that is run every time that basically the condition is checked and we run the loop. Then we open some curly braces, and inside these curly braces we put the actual code, in this case code, and then we put all the code that we want. So this is how we use and initialize a for loop. An example of this could be the following. So suppose that we want to print all numbers up to from 1 to 10. So of course we could do just funct print line 1 and then funct print line 2 and so on. But notice how basically how time consuming first of all this is to write manually this code, and also how untidy it will look like in the end. And also notice how not scalable this is. So suppose we now want to print 50 numbers, 1 up to 50, you have to write other 40 times print ln for the other values. Whereas let's now look how we can do that with for loops. So we will start by saying for, then the initialization condition, this will be run once when we start the loop. So we will initialize a variable I to 0. And also initialize and declare. Remember that we said we want to print all numbers up to 10. So the condition will be that I has to be less than 10. And then each time that this condition is met, we increment I by 1. And then inside of here, so this is the code that is run every time this loop is executed, we print I. Let's see what happens. As you can see, we get 0, 1, 2, 3, 4, up to 9. Actually, if you want to include 10, because before we wanted to, in the original problem that we had, we wanted also 10 inside, we will put 1 here instead of 0, and let's see what we get. 1 up to 10, as you can see. And so this is how you use for loops. You can also have nested for loops. So now let's delete this and let's think of a problem for which we want to use a nested for loop. So for example, consider the following problem. Print out all the elements of the set, for example, 1, 2, 3, Cartesian product with 1, 2, 3. So you want to print all ordered couples, for example, 1, 2, then 1, 3, then 2, 1, then 2, 3. So how can we do that? We will use 2 for loops. So we will first use a for loop starting from 1, going up to 4, and each time we increment it. And then we will use another for loop inside with the same values, but for another variable j. And then we will print out to the console from print line. Actually, let's use printf. We will print out the following. So we want to print it as a tuple notation. We could say a couple of elements. And then in here we will put I and j. So let's see what we get. As you can see, we get 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, and so on and so forth. So we got what we wanted. So now we see how we can use for loops, and these are basically just, if you come from other languages, the classical for loops that you also find, for example, in JavaScript, in Python, in Java, and C, and so on. But here in Golang, we will have to use for loops also to do what are known as while loops. But let's now suppose that we want to run something until something is true. So for example, let's set a variable, maybe, well, I don't know, like variable, var AB is equal to 25. And so suppose that we might want to run a condition, so something until AB is greater than 20. And so, for example, we could print out variable is greater than 20. So now what we will get from this is an infinite loop. In fact, we can try and run this. As you can see, we get an infinite loop. So in order to make this loop not infinite, we might try, for example, and decrement the value at each iteration, like this. And also notice that in Golang, just like in many other languages, you use ++ to increment the value and -- to decrement it. So in this case, we're decrementing it. And so let's try again and run it. As you can see, we get only 5 messages printed out to the console, because let's see what this for loop actually does. It first checks the value. So the value of the variable is initialized to be 25. Then here the loop checks if it's greater than 20. Well, 25 is greater than 20. So it runs this, it prints this out, and then decrements it. And 25 becomes 24. Then it runs this again. So AB, which is 24 now, is greater than 20. So it runs this again. And then AB becomes 23 because it gets decremented again. And so this proceeds on and on until it gets 21. 21 is greater than 20. This gets printed out. 21 minus 1 is 20. And so we get the last iteration, which is when AB becomes 20. Then AB becomes 20, but 20 is not greater than 20. And so basically the for loop finishes. And then it proceeds with the execution of the program. So for example, if there was other code here, it would have been executed. We can try and make an example. So for example, here, other code. As you can see, when you finish a for loop, then the program just keeps running, executing the code afterwards. And so this is how you work with for loops in Golang. And you can also make infinite loops. So without specifying condition, like this, you can just show for. And then here, you can just inside for example, the code you want to print out. So for example, let's say for, and we will say here infinite loop. Let's see what we get. As you can see, we get an infinite loop. This is very useful, for example, if you want to make some terminal-based programs where you want to rely on user input and you want to basically have an event loop, for example, for your mini terminal game or whatever. And so this is how you initialize an infinite loop without being based on a condition. And lastly, we will now see how loops can also be used to access values of a slice or of an array. Let's consider the case of a slice. So let's initialize a slice equal to, for example, a slice of integers. Actually, let's put it equal to a slice of strings. Value 1, then value 2, and then value 3, for example. So str 3 is strings. So now we can use a for loop to iterate through the slice. So one way in which we could do that is, for example, to say I initialize it to 0. Let's say I less than the length of the slice, then I++, and then we could just print out the console the element at the index I of the slice. And so we get all the elements, as you can see, value 1, value 2, value 3. But another way to do this, and this is maybe faster to write, is to use the for range loop. So how can we do that? We will say for, then here we need to specify 2 elements. That is the key value pair, so key and value. And then we will use the colon equal range, and then we will specify the slice inside of which we want to loop over. And then let's try to print this out. Let's see what we get. As you can see, we get out the same thing because we get the values. But this time we also had the keys, and the key is just the index to which you can find the specified element. And so this is also another way of looping through through a slice using a for loop. So you might also want to print out just the elements, or maybe just the keys of a slice. By keys, of course, we mean the indexes. So if that is the case, then you can just substitute the value that you do not want, and maybe you remember because we did it also in the earlier lectures, with this underscore. Because of course, if you try to just take it regardless and then don't use it, then the Go compiler will throw an error. So in order to discard, maybe in this case the key, maybe we just want to print out the values of the slice, we can just do as follows. So put an underscore in place of the k, we will just get the values printed out. So with this said, I think we have now said enough about for loops, and in the next video we will start looking at another very important concept in Golang, that of functions. So if you come from other languages, maybe you're already familiar with the concept of functions. But regardless, in this video we're going to introduce functions as if you never heard of them. So throughout the series we already worked with functions implicitly, because as you can see here, this keyword here, func, in front of the keyword main, is actually a keyword used to designate the sort of a function. And in fact, the function main with which we have been working with for the entirety of this video series is actually a function. But now let's try to explain what a function is. So in computer science, actually there's a more subtle distinction between functions and procedures. So now we're going to define both. So what are procedures? So procedures are just a block of reusable code, which however does not have an output, we could say. So in languages like C, or like also in like Golang, a procedure is represented by a void function, also known as a function that returns nothing. Okay, whereas a function is basically something which takes an input and gives out an output. So in principle, we, of course, practically speaking, we use both functions and procedures as ways to basically write code more compactly by writing these blocks of code that we can then use. But again, the difference is that functions take an input and then return an output via the return keyword, whereas procedures actually not return any output. This distinction is more, we could say, in languages like Pascal, if you've ever used it. If not, it's just an historical note. In languages like Pascal, there's more emphasis on this distinction. In languages like C, we just have functions, and in Golang as well, we just have functions. So when we will have an output, we will have properly what is called function. In the case in which the function returns void, that just means the function returns nothing, then we have a procedure. So let's start and say, well, we have seen that a function is basically a block of reusable code that takes an input and then spits out an output via a keyword that's called return. And then this function can be called inside our code, and executes all the code that is inside the function delimiter, and this makes the code way cleaner, and this is why they're so useful. But now let's see actually how to define a function. So in order to define a function, we need first to use the keyword func. This designates the start of a function. Then we're gonna specify the name of the function. So in this case, let's call it, for example, test function. And now notice that when you will work with more big programs, when you want to write, for example, in a file, a function that is also exported, you want to write it with a capital letter, as well as variables. If you want to export a variable to other files, you have to write them with a capital starting letter. In this case, we're still working, with a single file, so we don't have to worry about it. And technically, you're still working, if you have not installed yet a Go environment on your computer. We will do that once we have covered the basics. You're probably still using, as I recommended in the description, the Go Playground website to, we could say, experiment these features of the language. So to define a function, we basically first start by first defining the name of the function, then putting these two braces here, and then we're going to put behind inside curly braces the actual code of the function. So now we said the functions can have an input and can produce an output. Okay, but how can we designate it? Because at the current state, our function does not take any input, and also it returns no output. So in order to take an input, we are going to specify it inside the these braces here, these parentheses. And in particular, we're going to designate the output that it's going to take with a name, for example, x, and then we're going to specify its type. So let's suppose we want to write a test function that takes in two integers and then prints out to the console their sum. So in order to denote that we're going to take two integers as an input, we're going to use an identifier to denote the first input, then specify its type, then we use a comma, and then another identifier for the second input as well as its type. So we have said that we want to print out to the console their sum. So what we're going to do is going to print out x plus y. But notice we have not returned anything, so the function actually does not have a return value. For this reason, this function returns void. This is actually, technically speaking, a procedure. So let's now, in order to call our function, we need to call it inside our main. Because as we said earlier, the difference between a scripting language and a programming language, in a programming language, as for example Golang, in Go, main is the main entry point of the program. That is where the code that gets executed will be written. So in order for us to execute our function, we need to call it inside the main entry point. And inside the main entry point, we're going to call test function with 5 and 10. This should print out to the console 15. Let's see if it works. As you can see, we get 15. So this is the basics of how to write a procedure, so a function that returns nothing. But what if we want to return something from this function? So let's suppose now that we not want to print this value, but rather we want this function to return their sum. So in order to specify that this function is going to return a value of a specified type, we need to denote it by putting the type that is going to get returned in front of the name of the functions after the parentheses, just like this. And then we're going to return the value that we desire, in this case x plus y. Now that we have to return this value, for example, we can store the result, the output of this function inside a new variable, and for example print it out to the console. So let's see what the result will be now. As you can see, it will be 15. But now the function actually returns the value. So we have it, basically when we call the function, we can store it, for example, inside a variable. And then we can print our variable out. But we can also do other things with that variable. For example, we can print out that variable plus 7, and then we will get 22, for example. That's an example of something we can do. And now, of course, you can write also functions that can, for example, take strings as an input. So you can say print a string, something like that. Then it's going to take a text string, and then it's going to return nothing. It's just going to print out to the console. It's just going to print out console that string. So for example, in this case, let's actually call it. So for example, print string of hello, and as you can see now, the output will be hello as intended. So these are the basics of functions. Now we can also have another way of returning values to functions. So instead of saying here, for example, the type, let's suppose that now we want to return a string here, and let's change it to, for example, say hello, and we're gonna, for example, return a string that's gonna be hello and then the name of the person that we're gonna pass in. Well, what we can do is we can actually define the variable that's going to be returned precisely here and specify its type. So for example, we can already specify here the name of our return value that can be output, and this is an identifier, so you can put an arbitrary name, for example type string. Then we're going to put the output equals to hello plus then the text, for example, then return. And as you can see here, we do not need to specify what we return because it's already specified up here. And then by, for example, calling this function, say hello, actually let's assign it to a variable x, then let's from print line x, let's see what we get. We should get hello Jacob, as you can see, as intended. And so this is also how we can use named output values. We can also have functions that return more than one value. For example, let's define a function calculator that takes two integers and then returns their product and their sum. To specify that we're going to have two outputs, we're going to use these parentheses and then specify inside the types of the two return values. So for example, we're going to call the return value number 1 z is going to be x plus y, and then w is going to be x times y. Then we're going to return z and y and then w, and let's see what happens. Also, to get the output of this function, we're going to need two variables inside of where we call it. So for example, if we decide to store the return values inside two variables, we're going to need two variables in this case because the output scores two integers. So we're going to say t and r is equal to calculator of 2 and 5, and so what we expect to get is that t will be equal to 7 and then r will be equal to 10. So let's try to print both of them out. Let's see what we get. And also another important thing, you can also combine basically multiple return values also with names. So basically, as we did before, we specified a name for our return value. For example, we can set this equal to z and this to y, so this to w. Then we can do this and we will get the same result. So with this said, we have said almost everything about functions, and in the next video we will look at another type of functions, and that is anonymous functions. So in the last video we talked about functions. In today's video we're going to talk about a specific class of functions known as anonymous functions. So what are anonymous functions? As the name suggests, an anonymous function is just a function that is anonymous, and that precisely means a function that does not have a label. In the previous video we all created functions with labels, such as calculator that took in, for example, two integers and returned out another integer and so on and so forth. So all of the functions that we created actually had a label, we could say. Well, anonymous functions actually don't have a label. They're just functions that do something, and well, we can assign them to a variable. We will see we can do that, but by themselves they actually don't have a label, and we can also call them on the spot. That means the place where we write them, we will be able to call them immediately. So let's start by seeing how we can, we could say, how we can write an anonymous function in terms of syntax. So in order to create an anonymous function, let's first try to create an anonymous function and assign it to a variable. Let's for example call this variable get product, and then of course we're going to use the colon equal operator, and then to specify that we're starting an anonymous function, we just use the keyboard func, and then immediately after specify the type of inputs that you're going to get. So now suppose that we want to write a function that gets the product of two integers. So we can say a int and b int, and then it's going to return an int. Now notice here that also a faster way to write our input is just to say a and b both of type int. This actually will work. This also will work if you try to compile it like this. And then inside of here, we can, for example, say return a times b. Now, if we try to print out the, for example, get product of 2 and 9, let's see what we get. As you can see, we get 18 as expected. Another thing that we can do is also call the implicit function that we define on the spot. So now let's try to define, for example, let's try and define an implicit function that takes, for example, an integer and prints it out to the console from the print line a. And now let's call it with value 2. Let's see what happens. As you can see, we get 2 because with anonymous functions we are able to call the function on the spot. So here we define an anonymous function, a function without a label, and then we called it immediately. Now that we are comfortable with anonymous functions, we will look also at how we can return functions from a function. So yes, when we use functions, we can also set functions as a return type for functions. Let's try, for example, to write a function, you could say function 1, that takes in, for example, a number, or actually let's take in a string and returns out a function. And now to specify that return type is a function, we're going to use the func keyword and then these braces here. With this, we're going to specify that we are going to return a function that takes in no input and also returns nothing. So it is a function that returns void. And now to specify what we're going to return, we're going to use an anonymous function. For example, we're going to say func, and then inside the code will be, for example, printf, or maybe print line, just the text that we passed in. And now inside of main, we can say print text, is going to be colon equals function 1 of, for example, hello world, and then we're going to actually execute the function. So this print text variable that we have here is actually a function. Why? Because we're setting it equal to the output of function 1. Output of function 1 is a function, in particular an anonymous function, the following one, which will just print out the input of the function 1. Once we have done this, we will then call the function print text, because it is an actual function in its own right. And so by running this, as you can see, we will get hello world as expected. So with this said, we have said enough about functions, and in the next video we're going to look at some other important keywords in the Go programming language. Today we're going to look at the continue and the break keywords in loops. So 3 videos ago we already looked at loops, specifically for loops, which if you come from other languages, we've also seen that for loops can be used to make, in Golang there are no do while and while loops, so we're going to only use for loops. And we have seen that we can create infinite loops, and also loops, conditional loops, such as a greater than 5, and then classical for loops that have an initialization condition, basically a condition that gets checked, and then a post condition that gets run every time, such as this one, for example. But when we work with loops, there are many keywords there are also some keywords that can be used in order to basically control the flow of the loop ourselves. And these are continue and break. The first one that we're going to look is the break keyword. So the break keyword just breaks the loops. That means that whenever it is encountered, the loop will stop looping. So let's suppose that we have an infinite loop. Let's define a variable here and initialize it to 0. So for example, let's say 4. And every time this infinite loop gets executed, we're going to increase our variable a. But then we're going to have a condition, and that is if a is equals 10, then we're going to break the loop. Let's now see what the output of this program is. As you can see, it is all the values up to 10, because once we hit 10, so once a is equal to 10, then we're going to break the loop. As we could see, the loop was basically, the loop finished. So we exited the loop. Another keyword that we can do is, for example, the continue keyword. So what the continue keyword does is it just skips an iteration of the loop. That means that we basically skip. And what that means is that basically when we encounter the keyword, we skip back to the next iteration of the loop. For example, we might say, well, we're going to add, to increment a, and then print it out. But what we're going to say is, for example, we're going to print it out if a is equal to 5. Then instead of printing it out, we're going to continue. And else, we're going to print the value out. So if we now run the same program, as you can see, we will have that 5 will be skipped. Why? Because if a is equal to 5, then the continue keyword is met. That means that we're going to skip to the next iteration of the loop. Then, as before, we kept the break condition at the bottom. That means that once a becomes 10, so once we reach 10, then the loop finishes. So we stop the execution because we encountered the break keyword. So with this said, we are going to conclude this video here, and in the next one, we're going to look at another important data structure in Golang, and that is maps.